Greetings everyone, welcome back to General Chemistry. The topic for today is electronic structure. Let's just get straight to it. Let's move on to our good old handy dandy document camera and let's start talking about this. So, electronic structure of the atom, how electrons are distributed around the nucleus of an atom. We talked about the structure of atoms a while back. I think it was probably in the very first video, actually. And we talked about the planetary model of the atom, sometimes called the Rutherford model or even the Bohr model. So there are some differences between Rutherford and Bohr, which we will talk about. But for as long as most chemistry students can remember, they've been taught that electrons exist in these orbits around the nucleus of an atom, kind of like a miniature solar system. And you can have 2 electrons here, you can have up to 8 electrons here. In the next ring, you can have up to 18 electrons, and so on and so forth. So the electrons supposedly just move around the positively charged nucleus like the planets revolve around the sun. Well, kind of, but not quite. You see, physicists were kind of upset with the original mini solar system description of the atom that was given by Rutherford. Ernest Rutherford was the one who used beams of alpha particles. He fired them at a piece of gold foil, and it allowed him to discover that, contrary to the popular belief at the time, the atom was not a solid object. It was mostly made of empty space. So Rutherford proposes this planetary model, and Bohr kind of sticks to it, but there are a couple of differences between the two. And not in the terms of how the system looks, but how the system behaves. So, physicists were upset with the Rutherford model because if you're going to have electrons moving around in fixed orbits around a nucleus, then when they move, they're going to have to release energy. They're going to have to release some energy when they move around. And if they release energy and they lose energy, then they're going to slow down. And as they slow down, what is supposed to happen, what's supposed to happen if they slow down is that eventually the positively charged nucleus will be able to pull them in. Opposite charges attract, after all. So what we would see is the electron starts moving in smaller and smaller and smaller and smaller circles until it just comes crashing into the nucleus like that. At least that's what was supposed to happen. And essentially what this means is that atoms would just collapse in on themselves and shrink. But we know this doesn't happen. We know that materials don't just spontaneously condense. So what's going on? Well, Bohr proposed a fix for this. Niels Bohr. He proposed a fix for this. He kept basically the same shape, but he said that it's impossible for electrons to come crashing into the nucleus because they can't lose energy gradually like what would have to happen for this spiral thing I drew. They can't just lose the energy gradually. They can only gain or lose energy in discrete chunks is what Bohr proposed. So Bohr proposed 3 key items. Number 1, Fixed orbits, so we still have fixed orbits at specific locations. You can't have an electron orbiting, say, right here between the first and second orbit, for example. You're not allowed to have that, so I guess I don't have an appropriate color, but that's not allowed. So you can only have electrons existing in one of these predetermined orbits. So Bohr kept that. Second thing Bohr said is that each orbit is associated with a specific amount of energy. Is associated with a specific amount of energy. Whoops. Of energy. There we go. So we will often refer to the energy of an orbit, but know that the orbits themselves are just places in space. They don't actually have energy. What we mean by the energy of an orbit is the energy an electron would have to have if it is in that orbit. But each orbit is associated with a specific amount of energy. So the first orbit has a certain amount of joules of energy. The second orbit, the electrons in there would have a specific amount of joules. The third orbit, a specific amount of joules, and so on and so forth. And finally, Bohr said that electrons can move between orbits. The word that we typically use is transition, but electrons can move between orbits by absorbing or emitting the correct amounts of energy. Correct amounts of energy, and I don't know if you can see that on the screen. I'll check after I finish writing. Yeah, you can see that. I mean, if you heard it, you don't even need to see it, but you know, having something to look at is good. Let's see, where do I want to go from here? So, for example, let's say, and I'm just making numbers up here, let's suppose that you have an electron right here, has an energy, actually, you know what? Here's what I'll call the energies. I'll call the energy of the first orbit E1, the energy of the first orbit E2, the energy of the third orbit E3. Not to be confused with the gaming convention. Okay. So let's suppose I have an electron and it wants to move up from the second orbit to the third orbit. How much energy would it need to absorb? Well, it would need to absorb an energy equal to the difference between E3 and E2. So the change in the electron's energy would have to be equal to the difference in energy between the third and second orbit in this case. And I'm using the absolute value just to be on the safe side, but you know, if you're moving from an orbit that's closer to the nucleus to an orbit that's farther from the nucleus, to get farther away from the nucleus, an electron needs to absorb energy. On the other hand, if you are at an orbit far away from the nucleus and you want to move closer to the nucleus, then you lose energy. So the closer to the nucleus, the lower the energy. And for the physicists out there, what I mean by energy here is the total mechanical energy, both the electric potential energy and the kinetic energy combined. So E represents total energy in this case, total mechanical energy. Okay, so how do electrons get or lose that energy? In what form is that energy absorbed or emitted? Introducing the concept of photons. If you want to learn about how photons were discovered and why they were necessary, then you might want to take a physics course, but I don't want to dig too deep into the physics because this is supposed to be chemistry after all. But yeah, if you look at light, you might think of light as this continuous stream, this wave that doesn't seem to have any gaps in it. Right? It's just all one big long stream. Well, it turns out that if you quote-unquote zoom in on this, then you'll find that light actually looks something more like this. So there was this big debate among physicists that lasted for decades about the true nature of light. Actually, not just decades, probably well over a century, maybe 2 centuries. I don't know my history all that well. But I know that for a very, very long time, chemists and physicists had debated the true nature of light. Well, actually, light is more of a concern for physicists, so maybe the chemists weren't that involved in it. But yeah, first we had Newton claiming that light was a bunch of particles, which he called corpuscles, and if you want the spelling on that, it's C-O-R-P-U-S-C-L-E-S. Corpuscles is what Newton called them, particles of light. Christian Huygens insisted that light was more of a wave because Huygens observed that light seemed to do a lot of the things, if not all of the things, that waves did. So in came James Clerk Maxwell, who quote-unquote resolved it with his electromagnetic theory, claiming that light exists solely as waves, and that was what the physicists believed for a while, until they started observing some weird, screwy phenomena. Well, they weren't exactly screwy, it's just it looked screwy to them. One of these was blackbody radiation. They noticed that blackbody radiation doesn't seem to reflect what the equations would predict if you treated light as a wave. So blackbody radiation, when they did the experiments didn't agree with their math. Same thing with the photoelectric effect. And the third thing, which is what we're going to focus on, is atomic spectra. So these were 3 key experiments that showed physicists that something about light isn't making sense. And as for blackbody radiation and the photoelectric effect, you can learn more about these if you take physics. Specifically, in high school, you can take AP Physics 2. In college, if you take the 2nd semester of an algebra-based general physics course, that's usually where this would be covered. But if you're taking it in college, make sure to read the course description and make sure that it includes modern and atomic physics. Otherwise, you're not going to hear about the photoelectric effect in your physics class. Anyway, they started, examining these three situations more closely, and eventually the concept of the photon was born. Eventually, the concept of the photon was brought into the fray, and we started thinking of light not as a continuous stream like this, but more like a bunch of little wave packets, a bunch of small wave packets that are being sent back to back, so it seems like they're a continuous stream, but they're not. This is kind of the same thing as when you take a look at a really high resolution digital photo and you see how it's all smooth and it's got anything that's circular, looks round and has nice curves and everything. But then you zoom in on it and you realize that it's all blocky and choppy and made of little pixels. Well, photons are like the pixel equivalent for light. Photons are like the pixels of light, quote unquote. Photons, you could say, are the quanta of light. Quanta, now there's a new word. Quanta is the plural of the word quantum. A quantum of something is basically like the smallest unit of something. So photons, I probably should have written that with an S. Photons are quanta of light. But yeah, a quantum of something is basically like the smallest possible unit of that thing. For example, a quantum of electric charge is an electron or a proton, or more specifically the charge of an electron or proton. So the elementary charge, which is equal to 1.609 times 10 to the negative 19 coulombs of charge. This is the smallest possible charge that you can have. So if you had to have a charge of, for example, 0.9 times 10 to the negative 19 coulombs, if you wanted to have this much charge, it would be impossible. Impossible, because to have that much charge, you'd have to have a little bit more than half of a proton, and you can't do that. Impossible. So yeah, charge is quantized. Charge is quantized, light is quantized. Basically, anything and everything you can imagine is said to be quantized. Quantized, so you don't have all the real numbers as possible values for anything that is quantized. Imagine, for example, the difference between going up a ramp versus going up a staircase. I probably should have left more room for that. Where do I want to put this? Tell you what, I'll put it down there. Right down there in that bottom left corner. So think of the difference between climbing up a ramp versus climbing up a set of stairs, or going down a set of stairs for that matter. Okay, that's my best attempt at drawing a staircase. So, in the case of the ramp, you can be literally anywhere on the ramp. Any possible place on the ramp, you can be there. You can be here, you can be here, you can be here. You can be at any real number distance along the ramp between 0 and whatever the length of this ramp is. You can't do that with stairs. So with stairs, you can only be at specific places. You can only be, for example, on top of this step or on top of that step. You can't be halfway between two steps. So we could say that, let's say the height of every step on this staircase is, oh, I don't know, 5 centimeters. Let's say 5 centimeters of height. Let's say each stair step is 5 centimeters in height. Is that even realistic? Probably not. Okay, let's do something better than 5 centimeters. Let's do... I think 10 centimeters is good. Yeah, let's say 10 centimeters per step. 10 centimeters per step. Then you can't ever be 15 centimeters high, because then you'd have to be halfway between the first step and the second step, between 10 and 20, and that just can't happen. So you could say height is quantized, and a quantum of height for this staircase is equal to 10 centimeters of height. So you can only ever have multiples of 10. Whole number multiples of 10. Kind of the same thing going on with light, except there isn't really a specific... what's the word I'm looking for? There isn't a specific dimension. There isn't a specific measurement unit to go with photons, which kind of bothers me a little bit, but anyway, that's what quantization is. So anything that's quantized is basically something that can only ever be a whole number multiple of some minimum value. Imagine a world in which height was quantized such that... Actually, maybe we should still go with this quantum of 10 centimeters. Let's suppose that a quantum of height is 10 centimeters. Then that would mean that anytime somebody grew in height, anytime somebody grew taller, we would see them instantly grow 10 whole centimeters all at once. There would be no in between, and that would be a kind of weird world to live in. But in fact, height is quantized. There is a smallest length, and that smallest length, in case you want to look it up on your own, is called the Planck length. And basically every length you can measure in the universe has to be some whole number multiple of the Planck length. It just happens to be very, very small, so we don't feel like we live in a quantized world. Very much the same as with photons being perceived as a steady stream of light, or going back to my original analogy of a high-resolution picture. Just because there are pixels, or just because you see it smoothly, doesn't mean that it's actually smooth. It's just made of a bunch of tiny, what's the word I'm looking for? Digital image quanta called pixels. And because you have a lot of them, and because they're really small and close together, you can't tell that, you know, the world is more discrete rather than continuous. By the way, it's discrete, C-R-E-T-E, not discrete with a double E. There's a difference between these two words. When something is discrete, that means it exists in chunks, exists in discontinuous chunks. Can I even fit that word in there? Discontinuous chunks or blocks or parts or steps or whatever word you want to use to fill in that blank. So that's discrete, E-T-E. The other discrete, when you're being discrete, you're being quiet, or am I about to misspell quiet? Quiet. Let me start that over. When you're being discrete, you're being quiet or secretive or hush-hush in general about something. That's why they say at the beginning of a graphic video or movie that viewer discretion is advised. They're talking about this version of discrete. Anyway, so photons are a thing, and because photons are a thing, we can calculate the energy of an individual photon. We don't have to worry about the energy of an entire stream of light. We can just worry about the energy of individual photons within a stream of light. And the equation that we use in order to determine the energy of a photon is really simple. The energy of a photon is simply equal to a constant called Planck's constant times the frequency of the photon. Planck's constant has a value. Planck's constant has a value of 6.626 times 10 to the negative 34 joule seconds. But I also mentioned something else in here, which is frequency. So the symbol that's being used for the frequency of a photon, the frequency of the radiation that it's a photon of, is represented by the Greek letter nu. In physics, we just use F like sensible people, but in chemistry, for some reason, we use the Greek letter nu. So, Greek letter nu looks like a V, but it's not a V. It's got that, hook at the front, or whatever you want to call it, a serif, I think is what it's called. But yeah, Greek letter nu represents frequency. Represents frequency. So, frequency is related to two other things that are properties of a wave. So we should really get into waves and what they are before we proceed any further. Let's talk waves. Let me draw two graphs. One is going to be vertical position in meters versus horizontal position in meters. And my other graph is going to be vertical position in meters versus time in seconds. And on these two graphs, I'm going to draw a pair of generic waves. Let's see, what color should I use? I'll use magenta. So, let's see, we've got, here's one wave. Well, actually, it's multiple waves. We'll talk about what defines a wave in a bit. And then I'm going to try to draw exactly the same thing here. I hope it all lines up, but you never know with my drawing skills. Yeah, it's pretty well lined up. Okay, so let's talk about the components of a wave and some of the main properties of a wave before we go any further with our talk of photons. So, every wave, at least every transverse wave, this doesn't apply to longitudinal waves, but you don't need to worry about longitudinal waves in chemistry. That's a physics thing. But for us, for every wave that looks like this, it's going to be made of a bunch of peaks, which are called crests, and a bunch of valleys, which are called troughs. valleys which are called troughs. I'll usually just call them peaks and valleys because it rolls off the tongue easier, but the official terminology is crest and trough. So the definition of one full wave, is equal to one full, I probably should have used an equal sign, but one full crest plus one full trough plus one full trough. If you have that, you've got one whole wave. So for example, I can have this whole crest right here and this whole trough right here, and then I can say that everything from here to here is just one whole wave. So that's just one wave right there, one full peak and one full valley. Of course, I don't have to start at the beginning of a peak and end at the end of a valley. I could start at the beginning of a valley and end at the end of a peak. Or I could even start in the middle of one peak and just move to the middle of the next peak. So I could start here and go to here. I could go from here to here because that would give me half of a peak plus one whole valley plus half of a peak. Half and half, that's one full peak plus one full valley. There you go, that's another whole wave. So then, if I have my wave on a vertical versus horizontal position graph, then I can calculate the change in horizontal position between the beginning and end of a full wave to figure out something that's known as the wavelength. Let me go ahead and put some numbers on here. So let's say that's 0. We'll say that this is 2 meters, 4, 6, 8, 10, 12, and so on. So that's labeling my x-axis. So if I take a look at one full wave, just pick out one whole wave out of this. So let's just say the one that I had in blue. So it's going to be between x equals halfway between 4 and 6 is 5. So from 5 to 9, right? From 5 to 9, that's a distance of 4. So this distance right here is 4 meters. Well, that's what we would call the wavelength. The length of one wave, the length of one full wave in this example is 4 meters. Wavelength of 4 meters. So another Greek letter, lambda, L-A-M-B-D-A. There are some discussions between people online over whether or not you should have that silent B in there. I was just double checking the spelling on the internet and ran into this debate that I didn't even know was a debate, but apparently people disagree on the correct spelling of lambda. So that's a political question. I'm not going to dig into it, but if you want to fight over it in the comments or go online and find the places where people are debating it, you're more than welcome to do so. Lambda represents wavelength. Represents wavelength. Suppose you didn't have a full wave. Suppose you were given a graph where you didn't have a whole wave. What would you do then? Well, you would count how many waves you do have and simply divide by divide the distance spanned by whatever chunk of a wave you have, divide it by the actual number of waves. So if, for example, I had a wave that looked like, let me just draw a new one up here. Suppose I had this. and it just stopped here, and I was given these quantities. Let's say they counted by tens this time, so 0, 10, 20, 30, 40, and so on, and that should still be in meters. Then in this case, I have a wave or actually no, not even a wave. I've got a peak, which is half of a wave, and then half of a valley, which is half of a wave, or a fourth of a wave. So I've got 3/4 of a wave. So I've got 3/4 of a wave, and it's 30 meters in length. Then what I would do is I would take the total length, 30 meters, divided by the total number of waves, which is 3/4 or 0.75, and 30 divided by 0.75, what would that be? So it would be, I think, 40, if I'm not mistaken. Yeah, 40 meters. And I think you can easily see with this example, if I had continued drawing the rest of this wave, then it would have reached one full wave at 40 meters. But yeah, you can just take the total length divided by the total number of waves to get the wavelength. For frequency, you need to look at a position versus time graph. Frequency is equal to the number of waves passing by per second. Frequency is equal to the number of waves passing by per second. So if I were to number these, let's say counting by fives, so there's 5, 10, 15, 20, 25, 30, and so on. If I want to get the frequency, then what I would have to do is get the total number of waves passing by per second, and if in 1 second you don't get a full number of waves passing by, that's fine. Do what we just did with wavelength over here when you don't have a complete number of waves. We can just take, for example, let's say I want to do 20 seconds. Let's say I take these first 20 seconds over here, and I see I've got 2 waves in 20 seconds. I've got 2 waves, 2 full waves, 2 cycles in 20 seconds. Then what I can do is I can take the total number of waves divided by the total number of seconds. 2 over 20 is equal to 1/10. Equals 1/10, or 0.1 waves per second. Waves per second, or cycles per second. But waves aren't really a unit of measurement, so usually we'll just refer to this as 0.1 inverse seconds. We'll just refer to it as, where do I even want to write this? I guess there's only one place to write it. Which color should I use? I'll use this one. Actually, let me write it down here. I need that space for something else. So 0.1 waves per second can also be written as 0.1 inverse seconds. That's 0.1 1 over seconds. Or you can write it as 0.1 seconds to the -1, which is the same as 1 over seconds. We just call them inverse seconds. Or we can use the formal unit for frequency, the hertz, named after Heinrich Hertz, who, if I'm not mistaken, was the inventor of the radio? Or was that Marconi? I forget. But you can look that stuff up if you're curious. But yeah, 0.1 hertz, named after Heinrich Hertz. So a hertz is a cycle per second. 0.1 hertz is 1/10 of a cycle per second, or 1/10 of a wave per second. I should actually use the word cycle, because hertz can apply to things that are not necessarily waves but do repeat periodically in cycles. But yeah, so that's calculating frequency. You just take the number of waves divided by the number of seconds it takes for that many waves to pass by, and you've got your frequency. Now, wavelength and frequency are both related to each other through the speed of the wave. In order to calculate the speed of a wave, you simply multiply the wavelength by the frequency. Wavelength, which will typically be in meters in our examples, times frequency, which is going to be in inverse seconds. If I multiply meters by 1 over a second, I get meters per second, and those are definitely units of speed. In the case of chemistry, we're only going to deal with one type of wave, and that is the electromagnetic wave. Electromagnetic waves all travel at the speed of light. So for the speed, I'm going to plug in the value of c. And so we're left with c equals lambda times nu. Again, this is just for electromagnetic waves. For EM waves only. For EM waves only. And the speed of light, c, is yet another constant whose value is 2.998 times 10 to the 8 meters per second. Some teachers will round this to 3.00 times 10 to the 8, and that's fine, but this is the value I'm going to be using for the rest of this video, and I guess the rest of this general chemistry series. Okay, so now we've learned some basics about waves and frequency. Let me see. We've got the photon energy equation. Now that we know what frequency is, we can actually make sense of it. So let's see, since frequency is in units of hertz or inverse seconds, if we take Planck's constant, which is in units of joule seconds, multiplied by inverse seconds, the seconds times the inverse seconds would cancel out, and you would be left with joules. So yes, that is indeed going to give us energy. Okay, let's go ahead and make use of this. Actually, wait. Let me check what problems I have lined up. I might want to look at a couple of... Yeah, let's go ahead and do it. Let's go ahead and do a couple of problems before we move on. Okay, which problems would I like to do here? So let's go ahead and try the first one. It says the light produced by a red sign is due to the emission of light by excited neon atoms. Qualitatively describe... Oh, actually, no. We'll save that one for later. That's a qualitative question. Let me see. Okay, let's do numbers 2 and 3 then. 2 and 3 look like basic calculation problems. So it says an FM radio for number 2. FM radio station found at 103.1 on the FM dial broadcasts a frequency of 1.031 times 10 to the 8 inverse seconds, also known as 103.1 megahertz. What is the wavelength of these radio waves in meters? Radio waves are electromagnetic waves, and I guess I should talk about that before we go any further. So Let's talk about the electromagnetic spectrum. I knew I was forgetting something. The electromagnetic spectrum. Okay, so this spectrum is going to be on a logarithmic scale. I'm going to have increasing frequency as I go to the right. Increasing frequency as we go to the right. And this would mean then that the wavelength decreases as you go to the right. Because if we go back and look at this equation right here, the speed of all electromagnetic waves is the same. It's just the speed of light. So if the frequency goes up, the wavelength has to go down so that when you multiply them, you still get the speed of light. So the direction of increasing frequency is opposite to the direction of increasing wavelength. So we'll have increasing wavelength in this direction. Increasing wavelength. And let's see what kinds of radiation we have on the electromagnetic spectrum. Whether we call them electromagnetic waves or electromagnetic radiation shouldn't really matter. I use the terms interchangeably in the context of this video. But let's see, so right in the middle we'll have visible light, so the colors that humans can see. So I'm just going to have an arrow to that, visible light, which we will expand on in a minute. And then if I go above visible light in frequency, first I encounter ultraviolet radiation, then I encounter X-rays, then I encounter gamma rays. That's the Greek letter gamma, so gamma rays. And of course the spectrum continues beyond gamma rays, but we say that anything that's above X-rays is gamma rays because I guess we haven't discovered a need to give a unique name to any of the other types of radiation that are in that upper part of the electromagnetic spectrum. Maybe one day we will divide up the gamma rays into specific categories depending on what they're used for, but for now, anything above X-rays is considered gamma rays. Anything under visible light, well, the first band under visible light is infrared radiation. Below infrared, we've got microwaves. And then below microwaves, we've got radio waves. And basically anything under microwaves is considered to be radio waves until, again, just like with gamma rays, if we discover a useful category of waves within this bottom end of the spectrum, then we'll chop this up into individual parts again and come up with new names. That's just how things work in science. When there's a need to come up with a unique name for something, that unique name will be invented one way or another. Okay, so yeah, radio waves, whether it's FM or AM radio waves, are generally going to be lower in frequency than visible light. In fact, something you might notice, and this should make sense given the equation that says the energy of a photon is proportional to its frequency, you might notice that the names of the waves become more dangerous sounding the further up you go in frequency, right? So after visible light you go to ultraviolet, which we all know is pretty harmful, then X-rays, then gamma rays. The more frequency they have, the more dangerous their names sound. because, well, they are dangerous. High frequency means high energy, and high energy can cause a lot of damage if not used in a controlled and appropriate manner. But yeah, that's the electromagnetic spectrum and all the main categories or subcategories within the electromagnetic spectrum. Now let's zoom in a little bit on visible light. Let's zoom in a bit on visible light. Let's say I stretch this out. Let me use green for it. Suppose I stretch this out like so. Suppose I zoom in on that section of the electromagnetic spectrum. What would I see here? Well, with the lowest frequency, I would have red. So down here at the lowest frequency, I would have red, followed by orange, yellow, green, blue, indigo, and violet. You can remember the order of those colors by remembering the acronym Roy G. Biv, or if you prefer to read it backwards, Vib G. Yor. I prefer to read it as Roy G. Biv. That's in order of increasing frequency. So yeah, lowest frequency of visible light is red, highest frequency of visible light is violet, and actually when you know that, you can make sense of the names of the two categories of electromagnetic waves that surround visible light. Infrared is called infrared because it's below red in frequency, and ultraviolet is called ultraviolet because it is above violet in frequency. That's the reasoning behind the names. Now, depending on which textbook you consult, you'll get different numbers for what the highest and lowest wavelengths of visible light are. So, according to the last textbook I looked into, violet is at 400 nanometers, while red is at 750 nanometers. But I know I've seen other books that will say, that's not how you write nanometers, 750 nanometers. Anyway, as I was saying, I've seen other books that say visible light actually ranges from 380 nanometers to something like 850 nanometers. So it really depends on who you ask. It doesn't seem to be clear-cut because I get inconsistent ranges from different sources. Though I think the reason why the particular book I chose to get these numbers from decided to just keep it between 400 and 750 rather than including everything from 380 and after, and then everything up to, I think it was like 850. I think the reason they chose 400 to 750 is because if you subtract the two, you notice that the gap is 350 nanometers. 350 is easily divisible by 7, and I've got 7 different colors here, so I'm guessing that might have been the reasoning. I'm guessing the authors of that textbook wanted you to be able to just take the 350 nanometers from 400 to 750 and evenly divide them across the different colors. So 350 divided by 7 is 50, so you could say from 400 to 450 you've got violet, and then from 450 to 500 is indigo, and from 500 to 550 is blue, and so on and so forth. Now, that's not an exact science, but it's a pretty good approximation for whenever you're asked to give the color of a photon assuming that photon is actually within the visible range. If it's not within the visible range, then you can just say that it's somewhere below red or somewhere above violet and be done with it. But yeah, that's the electromagnetic spectrum and the zoomed in spectrum for visible light. Let's go back to that problem we were looking at. So an FM radio station has a broadcast frequency of 1.031 times 10 to the 8 inverse seconds. What is the wavelength of these radio waves in meters? Radio waves are electromagnetic waves. That means their speed is the speed of light. Therefore, I can do this. I can say speed of light, 2.998 times 10 to the 8, is equal to the wavelength, which is currently unknown, times the frequency, which they told us is 1.031, times 10 to the 8 inverse seconds. If I go ahead and run those calculations, 2.998 times 10 to the 8 over 1.031 times 10 to the 8 is going to be 2.908. 2.908. So lambda is 2.908 meters. And yes, radio waves do tend to be on the order of meters, or sometimes centimeters. Microwaves tend to be on the order of micrometers, hence the name. Infrared waves also tend to be in the micrometer range as well. Visible light, as we see, is in the nanometer range. Ultraviolet, some of it is in the nanometer range, and some of it is even smaller than that. X-rays, I believe, are in the angstrom range. That's something that we're going to see, so let's mention it up front. The angstrom range. So 1 angstrom, 1 angstrom, A-N-G-S-T-R-O-M, is sometimes written as 1A, and then there's like a dot above it. So 1 angstrom, which is equal to 1/10 of a nanometer, or 1 times 10 to the negative 10 meters. You could just call it 1/10 of a nanometer, but chemists like having the angstrom as a unit because apparently lengths not lengths, but like distances between nuclei and their electrons tend to be very readily measured in angstroms. Like angstroms seem to be a very fitting unit, a very appropriate unit for measuring the lengths of bonds between atoms or distances between nuclei and their electrons. But yeah, that's the angstrom. We will run into it later. X-rays tend to have wavelengths on the order of angstroms, and then gamma rays are even smaller than that. I couldn't even tell you. I guess maybe picometers, femtometers. Very, very short wavelength to compensate for their very, very high frequency. Anyway, radio waves are in the meter centimeter range, so 2.908 meters for a radio wave wavelength makes a whole lot of sense. Let's take a look at another one. Number 3, is it any different from the previous one? No, it's not. We'll skip it. Okay, what else do I need to look at from here then? Let's try number 5. So number 5 says we've got Light with a wavelength of 614.5 nanometers that looks orange. What is the energy in joules per photon of this orange light, and what is the energy in electron volts? Oh, I just realized I think I might have gotten one of my constants wrong earlier. Interesting. Anyway, let's take a look at number 5. So we are given the wavelength in nanometers, and we're told to calculate the energy. Energy is calculated from frequency, so first we have to calculate the frequency of the wave. If we know that light is going to move at the speed of light, so 2.998 times 10 to the 8 is equal to the wavelength, which was 614.5 nanometers. 614.5 times 10 to the negative 9 meters. 614.5 times 10 to the negative 9 meters times the frequency, which is currently unknown. Let's go ahead and calculate that. So calculator says 2.998 times 10 to the 8 over 614.5 times 10 to the negative 9. 4 sig figs over 4 sig figs is 4 sig figs, so that's going to be 4.879. Frequency is 4.879 times 10 to the 14 inverse seconds, or hertz. I'm just gonna write hertz because that's what I'm used to saying for units of frequency. Okay, now that we have this, we can multiply by Planck's constant to get the energy. So energy, let's switch to another color. Energy of a single photon is equal to 6.626 times 10 to the negative 34, that's Planck's constant, times the frequency, which is 4.879, times 10 to the 14. Don't need parentheses yet. Times 10 to the 14. Okay, now parentheses. Scribble that out. Okay, if I multiply that, 4.879 times 10 to the 14 times 6.626 times 10 to the negative 34, then I get, rounding to 4 sig figs, 3.233. 3.233 times 10 to the negative 19 joules. So that's the energy in joules, but they also asked us to calculate the energy in electron volts. And they say here that an electron volt is 1.602 times 10 to the negative 19 joules. I was pretty sure it was 1.609 because an electron volt is the elementary charge of an electron or proton times the times 1 volt, 1 joule per coulomb of charge, times the amount of coulombs that 1 proton or 1 electron would have. But yeah, is it really 1.602? Why on earth did I come up with 1.609? Let me Google it and double check real quick. Elementary, wait, I don't even need to Google it. I can just find it even quicker in the back of my book. This will only take a couple seconds. Let's see, elementary charge is... Wait, they don't have it here? Oh, there it is. Page just before the back cover. Elementary charge. It is 1.602. Then why was I thinking 1.609? Oh, I think I know why. 1.609 is stuck in my head because that's the number of kilometers in a mile. That's what it is. Okay. Good to know. Good to know. Anyway, back to the problem at hand. So I guess what I wrote back here was wrong. That should be 1.602, not 1.609. So correct this, it should be 1.602 times 10 to the negative 19 coulombs of charge. Anyway, back to the problem at hand. So they wanted us to get this energy in electron volts. We're not going to use electron volts in chemistry all that much, but it's a simple conversion problem. It shouldn't be too hard to do. 3.233 times 10 to the negative 19 joules times 1 electron volt over 1.602 times 10 to the negative 19 joules gives us 3.233 times 10 to the negative 19 over 1.602. That gives us 2.018 equals 2.018 electron volts. You use electron volts extensively in physics. We don't use them that much in chemistry. And by don't use them that much, I mean we don't use them at all in general chemistry. But this book likes to, broaden your horizons and help you connect chemistry to every other relatable topic possible. So sometimes we'll see questions like that. But there you go, 2018. Would have been phenomenal if I had recorded these last year. Okay, let's take a look at some other problems we might be interested in doing here. So we just did 5. Is 6 interesting at all? Yes, actually it is. So number 6 says, heated lithium atoms emit photons of light with an energy of 2.961 times 10 to the negative 19 joules. Calculate the frequency and wavelength of one of these photons. What is the total energy in 1 mole of these photons? What is the color of the emitted light? So pretty much asking everything they can ask for. Okay, so we are given the energy per photon is 2.961 times 10 to the negative 19 joules. And we are asked to find frequency, wavelength, energy per mole, and color. Frequency, wavelength, energy per mole, and color. Let's see. I guess I'll call this E photon. And I'll call this E mole. And of course, color. Okay, calculation time. So we've got the energy is 2.961 times 10 to the negative 19 is equal to 2.961 times 10 to the negative 19, the energy of a photon, is equal to the Planck's constant, 6.626, times 10 to the negative 34 times the frequency, which is currently unknown, divide. So we've got 2.961 times 10 to the negative 19 over 6.626 times 10 to the negative 34 is 4.469 times 10 to the 14 hertz. All right, find the wavelength. So we know the speed of light is equal to the wavelength times the frequency for any electromagnetic wave. So 2.998 times 10 to the 8 equals frequency times wavelength, so lambda times 4.469 times 10 to the 14. Let's see, 2.998 times 10 to the 8 over 4.469 times 10 to the 14, rounded to 4 sig figs, is 6.708. 6.708 times 10 to the negative 7 meters. The lengths that we get from this equation are in meters. If we want to convert to nanometers, divide by 10 to the negative 9 and we get 670.8. 670.8 nanometers. Okay. Let's see. So what is the energy in... Did they want kilojoules per mole or joules per mole? They didn't specify, but typically they will ask for kilojoules per mole. So let's see. We've got the energy in joules per single photon. So if I go ahead and just do a conversion, let's see, 2.961 times 10 to the negative 19 joules per photon. I can say there's 6.022 times 10 to the 23 photons in every mole of photons, Avogadro's number. Photons in every 1 mole of photons. And if I want to convert my joules to kilojoules, then I can say that every 1,000 joules is equal to 1 kilojoule. So multiply by Avogadro's number and divide by 1,000. 2.961 times 10 to the negative 19 times 6.022 times 10 to the 23rd is 1.783 times 10 to the 5. Divide by 1,000, that's 1.783 times 10 to the 2, or 178.3. 178.3 kilojoules per mole of photons. So 178.3 in kilojoules per mole. All right. And to determine the color, we can just look at the wavelength. 670.8 nanometers does fit within the visible range, so it should have a color associated with it. 670.8. So we said segment these in 50s, I guess. So 750, go down 50, and that puts you at 700. Go down another 50, that puts you at 650. So it looks like the high yellows to the low oranges. So I would say approximately orange would be the color. I would say that this is orange. But yeah, don't get too hung up on the color thing. When they ask you to predict color, it should usually be just a ballpark estimate. They don't want you to be super precise because, I mean, what shade of orange? There's no way I can tell you that. Okay, and yeah. So the question that we skipped was number 1. And that's actually going to help us segue into our next thing, because we're not done talking about the Bohr model of the atom. So question 1 says the light produced by a red neon sign is due to the emission of light by excited neon atoms. Qualitatively describe the spectrum produced by passing light from a neon lamp through a prism. So if you pass light from a gas lamp through a prism, you're going to get one of the strange observations, or, well, at the time it was considered strange. You'll get one of the observations that made physicists question the nature of light. And let me go ahead and switch over to the appropriate slide for this. So here's basically what's going on. So in that figure, you see a gas lamp at the bottom. It's that pinkish purplish tube. And in this case it contains hydrogen, not neon, so it doesn't directly relate to the question we were asked, but still. You've got a gas lamp using electricity to excite the electrons in that gas. You can move the electrons up into higher energy levels than where they would normally be. You can move them into higher orbits. And when they come back down from those higher orbits, they emit the energy back out in the form of light, in the form of photons to be specific. So when you send a beam of light from a gas discharge tube through a prism, the prism splits it, and you don't get, the full rainbow spectrum. You just get a couple of specific lines. You get, in the case of hydrogen, 4 specific lines at 4 specific colors. And physicists were quite perplexed by this in the earlier days of, the development of all this theory. So they wondered what was going on. They were expecting to see like a continuous stream of color, and instead they get these very distinct lines. And furthermore, some people started doing some math and finding a relationship that tells you the distance between these lines. So there was one guy, I think it was Johann Balmer, or was it Johannes Balmer? I forget. But there was this one guy, Balmer, who found a relationship. He realized, after doing some calculations, he realized that for these special colors, the specific wavelengths of light that do show up on a screen when you send them through a prism, he noticed that 1 over their wavelength is equal to a constant times 1 over 2 squared minus 1 over n squared, where n is any integer greater than 2. So 3, 4, 5, so on. So that was Balmer. And then other scientists started discovering very similar equations. Lyman had another equation that was pretty much the same thing. He had 1 over the wavelength equals some constant, turns out to be the same constant, times 1 over 1 squared minus 1 over n squared, where n is anything greater than 1, any integer greater than 1. And there were a couple of other scientists who also discovered similar equations, but each of them, they all had the same form of equation. The only thing different about them was what this starting number was. And that all eventually got resolved by Bohr's model of the atom, because Bohr gave us an explanation finally for what was going on. I don't think it was his intention. His intention was just to fix the problem of why on earth do atoms not collapse in on themselves? Why do electrons not crash into the nucleus? But yeah, the Bohr model, remember, it said that electrons can only move between orbits. Where did it go? Yeah, electrons can move between orbits only by absorbing or emitting the correct amounts of energy. And it turns out that the correct amounts of energy are actually associated with the energies of the photons of light that you see on that screen. If I pull the model back up, or I shouldn't say model, but the figure. It turns out that the photons that are represented by those 4 different colors of light represent 4 different energy transitions within the hydrogen atom, which Bohr studied. So they represent different transitions between different orbits within the hydrogen atom. So going back to, let me see here. What was it? Okay, going back to the concept of energy levels then. If you were to determine the amount of energy that an electron must have in order to be at a specific orbit, well, according to Bohr, here's what energy you would have to have at orbit number n. You would have to have an energy equal to negative 2.18 times 10 to the negative 18 times z squared over n squared times z squared over n squared. Z is the atomic number. It's the total number of protons in the nucleus. For hydrogen, that number is just 1. And n is just the number of the orbit. So the closest orbit to the nucleus would be n equals 1, the next one would be n equals 2, and so on and so forth. In fact, I think that's what I wrote back here, if I'm not mistaken. Yeah, E sub 1, E sub 2, E sub 3, and so on. So E sub n, n represents the number of the orbit counting outward from, starting from the nearest orbit to the nucleus. So this is what Bohr came up with. You might be perplexed a little bit by the negative sign. How on earth can you have negative energy? Well, the total energy of the electron is defined as the sum of the kinetic and potential energies, and kinetic energy cannot be negative, because if you remember when we did gas laws, we said kinetic energy was equal to 1/2 the mass times the speed squared, and I think for speed we used u, but whatever symbol you want to use for speed. 1/2 mass times speed squared. Mass can't be negative, and if you square the speed, that can't be negative either. So no such thing as negative kinetic energy, but you can have a negative potential energy. And because there's more negative potential energy than kinetic energy, overall the total energy of the electron comes out to be negative. And why on earth do we have negative potential energies? Because the problem with potential energy is that you can't calculate the potential energy at a specific location for an electron, or for a massive object for that matter. You can only calculate how much the potential energy increases or decreases between two locations. You can't find the exact potential energy for a specific location. So you just have to pick which place you want to use as your starting point. And what we use as the starting point is the ends of the universe, an infinite distance away. We say that at the far outer reaches of the universe, that's where we define potential energy to be zero, and the closer you are to the nucleus as an electron, the lower your potential energy gets. So if you're coming in from infinitely far away where you have zero energy, and your potential energy decreases as you get closer to the nucleus, then of course you can only ever have negative potential energies. This is illustrated in the following diagram. So you've got the lowest energy, and this is for hydrogen specifically, so Z equals 1. Energy is negative 2.18 times 10 to the negative 18 joules over, or times 1 squared over n squared. So lowest energy, negative 2.18, makes sense because you're just dividing by 1 squared. Next energy level, you're dividing by 2 squared, so it should be 1/4 as negative. Negative 2.18 divided by 4 should give us negative 5.45, and your power of 10 should decrease by 1. And yeah, the green line would represent negative 2.18 times 10 to the negative 18 over 3 squared. Yellow line is over 4 squared. Orange line is over 5 squared, and so on and so forth. And then that brown line at the top is just set to 0. It's at an infinite distance away, or at the energy level n equals infinity, at which point you could consider the electron to be completely outside of the atom and completely freed from the atom. In fact, if you want to transition from whatever energy level you're at up to infinity, if you want to eject an electron from an atom, if you want to, in other words, ionize the atom, removing an electron from an atom would make it into an ion after all, then you would just add in whatever amount of energy. You would add in the negative of the energy associated with the energy level that your electron is already at. So, for example, to make this more concrete instead of some wordy mumbo jumbo, if you wanted to remove an electron from the first energy level, or the first orbit, then you see that the first energy level is negative 2.18 times 10 to the negative 18 joules. You would have to add 2.18 times 10 to the negative 18 joules of energy to that electron so that it would have enough energy to jump from that purple line all the way up to the brown line at infinity. If, on the other hand, you want to make the electron jump to maybe not out of the atom, but jump from the first orbit up to the second orbit, then what you would have to do is calculate the energy difference between negative 2.18 times 10 to the negative 18 and negative 5.45 times 10 to the negative 19, and whatever that energy difference is, that would be the amount of energy you need to give the electron for it to jump up, or the amount of energy that electron would give away if it jumps down from level 2 to level 1. So, in fact, I have, let me see here, where did I put it? I know I have it here somewhere. Yeah, there we go. So I have this other diagram. This is, again, for the hydrogen atom. So all of those arrows represent all of the possible transitions that electrons can make within the hydrogen atom. And you'll notice for every upward arrow, there is an equivalent downward arrow. because it is possible to jump both up and down. So let's see here. What did I want to say about this? If we consider all of the possible jumps you can make from the second level, I believe, or between the actually, I'm not entirely sure. I'm not entirely sure which of these transitions match up to which colors in that line spectrum we saw earlier, but maybe we can do some calculations and play around with it a bit. Let me think. Yeah, I think I'll do some calculations once we get to some problems. But let's go back to this. So for our purposes, we're going to, for the most part, deal with the hydrogen atom. We're not going to deal with anything other than the hydrogen atom. And the reason for that is because, well, Bohr's model works great for hydrogen. It doesn't work so well for anything else, unfortunately. There are some problems with Bohr's model. It's not perfect. But as far as the hydrogen atom is concerned, so for hydrogen, Z is equal to 1. And if I want to calculate the change in energy for a transitioning electron, then all I have to do is take the energy of the previous level and the energy of the current level and subtract the difference between the two. So negative 2.18 times 10 to the negative 18 times 1 squared over n final squared minus 1 over, or 1 squared rather, over n initial squared. That should give us the change in energy when transitioning between two different orbits. Did I write this equation earlier somewhere? Because I feel like I did. No, I did not. At least not as far as I can tell. Okay, having, what's that word? It's not déjà vu. Is it déjà vu, or is it jamais vu? I guess it would be more of a déjà vu moment. Anyway, the change in energy for an electron that transitions from some initial orbit, n sub I, to some final orbit, n sub f, is simply the final energy it has, so this constant times 1 over n final squared, minus the initial energy it had, which is this same constant times 1 over n initial squared. Those of you who know your math already can see that, but just wanted to elaborate on it for those who are wondering where this comes from. I simply took, this is simply equal to the energy of n final minus the energy of n initial, where energy of n final and energy of n initial can be calculated from this formula up here, with z equals 1, by the way, with z equals 1. For all intents and purposes, as far as chemistry is concerned, you're going to have z equals 1. We might look at a couple of examples where z is not equal to 1, but those will just be for the sake of example. Don't expect to deal with cases where z is not equal to 1. Okay, so if we go ahead and do some calculations, let's go ahead and calculate the energy change for a particular transition within the excited hydrogen atom. And by the way, that word excited, I didn't really define it now, did I? So excited versus ground state electrons. Excited versus ground state electrons. Might as well get that out of the way before we do any math. So electrons typically will have the lowest energy that they can have within an atom. So hydrogen has a single electron, so it's a single proton orbited by a single electron, and that single electron will usually just sit around in the first orbit. We say that the electron is in its ground state in that case. But of course, if the electron moves up to a higher orbit, if we give it energy, if we excite it, then it can move up to a higher orbit, and then it won't be in a ground state anymore, it'll be in an excited state. So if I had a hydrogen atom that, let me just draw a second one. If I had a second hydrogen atom with an electron in the third orbit, like this, then we would say this hydrogen is in its excited state. The electron specifically is in an excited state. And yeah, that's what's meant by excited. At a higher energy level than normal. Normally, electrons will fill the lowest level energy orbits that they can fill, and then proceed and move on to filling the next highest, then the next highest, and so on. So lowest orbits, lowest energy orbits filled first. But you can, of course, change that by giving the electrons energy, and there are a couple of ways in which you can give the electrons energy. One such way is to fire a photon at an electron. So let's ask the following question. What wavelength of photon would I need to fire at a ground state hydrogen atom to get it to the excited state shown over here? So we've got an energy transition from n equals 1 to n equals 2. N initial is equal to 1, and the final is equal to, did I say 2? 3. Third level. From the first level to the third level. Let's go ahead and see what color photon needs to be absorbed, if it's even within the visible range to begin with. So if we go ahead and do the math, we've got negative 2.18 times 10 to the negative 18 times 1 over n final squared is 3 squared, or 9, minus 1 over n initial squared, 1 squared is 1. So if I go ahead and do that, I've got negative 2.18 times 10 to the negative 18 times 1 over 9 minus 1 over 1. That's going to be an exact number, by the way. 1/9 minus 1 over 1. And let's see, so 3 sig figs in, 3 sig figs out, since I'm only multiplying by exact numbers here. That's going to be 1.94 times 10 to the negative 18 joules. 1.94 times 10 to the negative 18 joules is the energy change. That's the change in energy. So if we absorb a photon if this electron absorbs a photon that has this much energy, it can jump up, it can make the exact jump from level 1 to level 3 in energy. Notice that this time the energy change came out positive, but change in energy can also be negative. If I started up here and I went down from the third level to the first, I would get negative 1.94, which just indicates that the electron would have lost energy, would have emitted a photon. So electrons can either jump up by absorbing photons, or they can jump down by emitting photons. So the energy of the photon, either way, is the absolute value of the energy change. Absolute value of the energy change for a transitioning electron is equal to the energy of the photon that is either absorbed or emitted during the transition. It's absorbed if the electron is transitioning upward, and emitted if the electron transitions downward. Okay, so moving on to another page, let's go ahead and figure out what frequency of photon we're dealing with. We had energy is 1.94 times 10 to the negative, was it 18? Yeah, times 10 to the negative 18 joules. If I set that equal to Planck's constant times the frequency, what do I get? 1.94 times 10 to the negative 18. Let me put that up there. 1.94 times 10 to the negative 18 over 6.626 times 10 to the negative 34 gives us, in this case I'd have to round to 3 sig figs, 2.93 times 10 to the 15 hertz. Wait, what did I do? Hertz. And if I calculate the wavelength associated with that, speed of light equals wavelength times frequency. So speed of light, 2.998 times 10 to the 8, divided by the frequency, 2.93 times 10 to the 15, gives us the wavelength lambda is equal to 1.02 times 10 to the negative 7 meters, which is equal to 102 nanometers, which is outside of the visible range. So this is a line that Balmer would not have observed, because Balmer, he came up with an equation for the visible range, right? And in fact, that shows Balmer's equation has n starting at 2, or actually n starting at 3, with the other n being fixed at 2. So Balmer wasn't able to find, wasn't able to detect this because he just wasn't looking for infrared radiation. He was looking for visible light. On the other hand, this would have been detected by Lyman's equation. Lyman's equation does cover for waves in the infrared range. And then there was another person who found an equation that works in the ultraviolet range, and another person who found an equation that works in the X-ray range. But we're getting closer to, or, well, actually, we're not getting closer. We're already there. We've finally found something that seems to explain what Lyman, Balmer, and others were observing. But, of course, we want something that we can actually see. So let's do another electron energy transition. This time let's do it again for the hydrogen atom, but let's do it from 3 to 2. let's do from n equals 3 to n equals 2. And I'll try to be quick about this one since we've already seen the process. So going from n equals 3 to n equals 2, we've got negative 2.18 times 10 to the negative 18 times 1 over, let's see, final squared, so 2 squared minus 1 over 3 squared gives us negative 3.03 times 10 to the negative 19 joules. And this does make sense that it's negative because we're moving from a higher level to a lower level this time. The electron is losing energy overall. It's moving from some negative total energy to an even more negative total energy. Okay, absolute value of that is the energy of the photon. So then energy of a photon, 3.03 times 10 to the negative 19 divided by Planck's constant, 6.626 times 10 to the negative 34, gives us 4.57 times 10 to the 14 for frequency. 4.57 times 10 to the 14 hertz. And then if we take the speed of light divided by that, 2.998 times 10 to the 8 divided by 4.57 times 10 to the 14, we get 6.56 times 10 to the negative 7 for wavelength. 6.56 times 10 to the negative 7 meters, which is equal to 656 nanometers. And 656 nanometers is in the visible range. It's between 400 and 750, or 380 and 850 if you prefer. Between 380 and 850 makes it sound more like a credit score. Those of you already in college might already be familiar with credit scores, both fortunately and unfortunately. Those of you in high school, oh, just you wait. The credit card companies are going to have all these almost filled out applications ready for you just to sign your name and send it back to them so that they can have you on the hook for the rest of your life. I mean, credit cards aren't necessarily a bad thing. It depends on how you use them, but if your initial response to getting a letter from a credit card company isn't fear, well, I shouldn't say fear, but what's the word? Skepticism, then you might need to find yourself some good resources for some financial education, or else you might be setting yourself up to ruin yourself. Anyway, 656 nanometers. I wonder if that matches one of the lines that we saw in the line spectrum earlier. Let's go ahead and see. Oh, would you look at that? That's the red line in that line spectrum for hydrogen up there. It's 656.3 nanometers to be more precise, but there you go. Then I wonder if we did calculations for other electron transitions within the hydrogen atom, would we get that light blue line, the darker blue line, and the violet line? Answer is yes, of course, you can get those. I guess you'd have to do transitions between, let's see, so we did from level 3 to level 2. I imagine you can do transitions between 2 and 4, and 3 and 4. And what would the fourth one be? Maybe 4 and 5? or 3 and 5 or something like that. I'm not sure. But yeah, you can you can definitely find a pair of ends, a pair of orbits between which an electron can make a jump and get a photon that corresponds to one of those 4 colors that you see for hydrogen. So those are the colors that you can see hydrogen emit, but those are also the 4 colors that hydrogen can absorb. So it actually works both ways. An absorption spectrum kind of looks like an emission spectrum, except it's basically the reverse. An absorption spectrum would basically have the entire colored spectrum, so all the colors would be shaded, except you'd have like a gap, a black line for where that first line in the emission spectrum is, and then another gap for the next line, and then you'll have the rest of the colors are showing, and then you'll have another gap, and then the rest of the colors showing, and then another gap. So you would have basically the whole entire strip, the whole entire screen would be like rainbow colored, except you would see 4 black lines for hydrogen, which correspond to the 4 colors that hydrogen absorbs. Those would be missing. You would just see streaks of black on what's otherwise a complete visible spectrum. So that's the absorption spectrum for hydrogen. It's basically just the reverse of the emission spectrum. Speaking of absorption versus emission, let's talk about other ways in which you can have atoms emit photons of different colors or absorb them. Let's talk about, let me see, where do I have it? Oh, well, I don't want to talk about it, but I just want you to know about it. So there's a really good YouTube video out there that shows you the flame tests for a whole bunch of different salts, a whole bunch of different combinations of ions. And right there I had it frozen at a clip where the guy was flame testing copper compounds, and copper compounds tend to give off a green flame. The colors of the flame tests are related to the emission spectra of the different atoms involved. So there you go. That's a video that you can go watch that has a bunch of flame tests. You can learn all the different colors of the flames of different ions. If you're preparing for the chemistry SAT, you might want to memorize the flame test colors of some common ions, because they might occasionally ask about that stuff. I wouldn't put it at the top of my priority list, but if you feel like you've studied everything you can study and you're not sure what else you need to read up on, memorize a couple of your flame test colors just in case they ask one of those questions. It'll probably be a question where they ask you to identify the substance, and they'll tell you, oh, this substance conducts electricity really well and has a shiny appearance to it, and when flame tested it gives off a green flame, and that's when you know, oh, it must be copper. And you'll see copper in the answer choices and you'll pick that. But it's not the top priority, just something that if you've already studied everything else, you're going to want to look into it. Anyway, that's flame tests, so kind of related to emission spectra. What else do I have? So when it comes to absorption, there's a little something that's actually not covered in any of the textbooks that I have, and the only reason I know about it is because I had to do it in my chemistry lab just once in college. But there's something called the Beer-Lambert law, or sometimes just called Beer's law. So what you're seeing right there is a beam of light being fired at a solution. So that red liquid stuff, that's just a solution, and I guess the solution is some sort of drink mix, like red Kool-Aid or something. But you have this beam of light being fired at a container. This container is called a cuvette. It's like a test tube. It's supposed to be really, well, it's supposed to be really transparent and not interfere with the light. Make it so that the only thing that interferes with the light is whatever you put inside of the cuvette. And cuvettes are usually designed to have a very precisely measured width or radius or diameter to them. So it's like a test tube, but built with a very specific diameter to it. And depending on factors such as the concentration of the solution inside the cuvette and how wide the cuvette is, the length of the path, basically, that the light has to go through, and of course depending on what the wavelength is and depending on what substance you actually have in that solution, the amount of light that makes it through, the amount of light that gets transmitted versus the amount of light that gets absorbed will vary. And this is all described by an equation which is called Beer's law, or the Beer-Lambert law. So let's dig into that really quick. So the Beer-Lambert law, it's a really simple equation. So the Beer-Lambert law, or Beer's law for short, says that absorbance, which is a measure of the amount of light absorbed, is equal to something called the molar absorptivity, represented by the Greek letter epsilon. Greek letter epsilon. This refers to the molar absorptivity, is what it's called. Molar absorptivity. Times the concentration, which they represent with C, times L, which is basically the path length or the diameter of the cuvette. And by the way, cuvette is spelled C-U-V-E-T-T-E. So that's what it's called. It's just a special kind of test tube. But yeah, so C for concentration. Where should I write that? I'll write it over here, concentration. And then this is path length, the length of the path that light travels through the solution. Okay, so that's the Beer-Lambert law. But if you noticed on that image, and by the way, this is a PhET simulation, so if you go to Google and just type PhET and then the word Beer's law or something like that, you can find this and play around with it yourself if you really want to. But yeah, in this PhET simulation, I had the detector only give me the transmittance as a percentage. I did not show the absorbance. We can calculate absorbance from transmittance. So in this example, we have a wavelength of 508 nanometers. Wavelength isn't part of the equation, so we don't need to worry about it. We have a concentration of, it looks like, 150 millimolars. So 150 times 10 to the negative 3 molars. Let me write that data down. So C equals 150 times 10 to the negative 3 molars, or I guess that would be 0.150 molar in other words. The path length is 1 centimeter. There's a ruler right under the cuvette if you can't see it. So the path length is 1 centimeter, which is pretty common. So path length is 1 centimeter, and centimeters are actually standard units for the Bohr's law equation. So no need to convert them to meters. We typically do it in centimeters. And to get absorbance from transmittance. So we're given a transmittance of 17.42%. We're given a transmittance, I'll call it capital T, of 17.42%. Okay, done copying all that down. Okay, so how do we calculate absorbance from transmittance? This is something that you fortunately will not have to deal with at all if you're doing high school chemistry. If you're doing college chemistry, you might have to do a Bohr's law question. But to get transmittance, absorbance, all you have to do is take the log of the intensity of the light originally divided by the intensity of the light that actually makes it through, the intensity of the light that comes out the other end of the tube. So intensity transmitted. But we don't have the intensities of the light, we have the percentages. And that's fine because the percent transmittance is really just equal to the transmitted intensity, I'll just call it trans for short, over the initial intensity of the light before it went through the solution, times 100%. That gives you the transmittance as a percentage. So you can also find the absorbance as the log, and that's log base 10 by the way, of 100% over whatever the percent transmittance is, which in this case would be 17.42. So log of 100 over 17.42 is equal to 0.7, let's see, hold on. So the 100 is an exact number, so I'll ignore that. 17.42, so that's got 4 sig figs. So I would need 4 decimal places in my log. That's one of the sig fig rules for logarithms and exponents. You'll learn about it later when you get to second semester stuff where you really need to use logarithms, so don't worry about it too much for now. But the absorbance in this case is going to be 0.7590. 0.7590. And yeah, that should be it. So absorbance is 0.7590. Now we can plug this in with the other values to solve for, I guess in this case we're solving for the molar absorptivity of that drink mix, some sort of red Kool-Aid or whatever. Okay, so we've got 0.7590. I'll write it over here. 0.7590 is equal to, and I see this marker is about dead, is equal to epsilon times concentration of 0.150 molar times a path length of 1 centimeter. We'll treat it as exactly 1. And so what we get is 0.7590 divided by 0.150 is 5.06. So we can say that epsilon for the drink mix is equal to 5.06, and that's going to be in units of inverse molars and inverse centimeters. So 5.06 absorbance units per molar per centimeter. And absorbance units are, well, just blank units. There are no units for absorbance. It's really just not even a ratio, but the logarithm of a ratio. We don't really have units for that. Okay, so there's a quick Beer Lambert law problem. Let me see. What else do I want to cover here? I feel like there was one other thing I needed to talk about before we could go ahead and do some problems. Oh, right, the failures of the Bohr model. So, the Bohr model did a good job explaining the reason why we get line spectra, but the line spectra that we got for other atoms, for atoms other than hydrogen, kind of followed Bohr's model, but deviated, and they deviated more and more as you started looking at atoms that had more electrons in them. So if you take a look at the following set of line spectra, so of course we've already seen hydrogen. There it is again. If you look at neon, calcium, and mercury, or sorry, no, that's not neon, that's sodium. I misread it. If you look at sodium, calcium, mercury, you see some more sophisticated spectra over here. If you look at sodium, first off, you've got a couple of double lines, a pair of lines that are right next to each other. So we've got a pair in the light blue region, we've got a couple of pairs in the yellow region, or I guess maybe that first pair is closer to green and that other pair is yellow, and then you've got an orange line all by its lonesome. If you look at calcium, it's got, what is that? It seems like a quadruple line in the bluish region. So you have all these lines that are really close together, and Bohr's model wasn't really able to explain this. Because if you have lines that are really close together like this, then that would imply that they are associated with very similar looking photons. Photons of similar wavelengths, therefore photons of similar frequencies, therefore photons of similar energies, therefore associated with similar sized jumps. Similar sized jumps, similar energy changes for the electrons. Well, there's two ways that you could have very similar jumps. One way is if you compared two electrons that are jumping from or to very, very high orbits. I shouldn't say very, very high, but relatively high orbits. So let me dig up the appropriate image for that. Yeah, right over here. So I think I pulled this image up before, but if this is the second time I've shown it, this time you'll notice something different. I circled two of the transition lines in pink. Those two transition lines represent jumps that seem to be nearly equal in size. The gap between the fourth energy level and the fifth energy level, the difference in their energy is a lot smaller than the energy level difference between 2 and 3, or between 3 and 4. So if, for example, we had an electron, let's say, transitioning from level 7 to level 3 versus an electron transitioning from level 6 to level 3, there would be very little difference in their energies. And that is one of the ways that you could get those double lines, those pairs of lines that are really close to each other that we just saw in the spectra of sodium and calcium and mercury. So that's one way it could happen. But there is another way that this could happen. Here's another way that things could happen. Let me do this over here. I think I've got a nice little space there. Let's go ahead and use it. So another way this could happen, so here's your energy, your increasing energy. Here's where I set the 0 line. So another way that this could happen, where you get those double lines, is if, let's say there's level 1, and then there's level 2. Let's say you actually have two transitions from level 2 to level 1. Let's say you've got two transitions from level 2 to level 1, but they are ever so slightly different because in reality, there isn't just a level 2, there's a level 2A and a level 2B. If I were to zoom in here, I might find a level 2A and a level 2B, so to speak. Two sublevels within a level. This is where Bohr's model kind of just crumbles, because Bohr did not allow you to have anything, you know, between two orbits, while the observations would suggest that you actually do have a couple of energy states just above and just below where Bohr would have the second energy level. And of course this also applies for the third energy level and the fourth energy level and so on. You actually do have energy sublevels, which are pretty similar in energy, but not quite identical. So that's another reason why you might get those strange pairs of double lines. There's also another thing that we get, which won't be explained until we talk about quantum numbers later, specifically the spin quantum number. But if I pull back up the picture with all those line spectra again, look at the line spectrum for sodium. Specifically, look at those bright yellow lines. One of those yellow lines is really thick. So when you get those thick lines, they're usually not going to be single lines. They're actually a bunch of lines that are so close to each other that you need a higher resolution to see the gap between them. So not only do we have pairs of lines with small gaps between them, we also have pairs of lines with even smaller gaps between them, so small that without a high enough resolution it looks like you just have one thick line. And those represent an even smaller energy difference between two transitioning electrons, which we will have an explanation for once we dig into the quantum numbers. Okay, so with that stuff out of the way, before we dig into quantum numbers and sublevels and all that stuff, let's go ahead and do a couple of problems just so we can get a feel for everything. Let me see, I think I want to switch. Well, I'll keep it on. Okay, we're done with that one. Let me see, do we want to do anything from here? Do I want to do anything from there? So I think 10 through 12 were what caught my attention when I was preparing. Number 10 says photons of IR radiation are responsible for much of the warmth we feel when holding our hands before a fire. These photons will also warm other objects. How many IR photons with a wavelength of 1.5 times 10 to the negative 6 meters must be absorbed by the water to warm a cup of water of 175 grams from 25 to 40 degrees Celsius? Oh, call back to the previous video we did. Okay, let's do this one. So if I go ahead and switch back to my camera here. Let's see. So photons have a... Wait, do I have their energy? No, I have their wavelength. So I'm going to have to calculate the energy. Wavelength is given as 1.5 times 10 to the negative 6 meters. From which we can definitely calculate frequency. Mass is 175 grams for the water. Specific heat of water, C of H2O, is 4.184 joules per gram Kelvin. I hope you remember that from the previous part. And then the change in temperature, we went from 25 Celsius to 40 Celsius, so that's a change. Delta temperature of 40 minus 25 is 15 Celsius degrees, or 15 kelvins. If you remember anything from the previous video, you might remember that Celsius degrees and kelvins are interchangeable when talking about temperature changes. Okay, so how many photons with a wavelength of 1.5 times 10 to the negative 6 does it take to achieve this heat change? Let's go ahead and calculate the amount of heat change. So Q equals mc delta T. So we've got 175 times 4.184 times 15. 175 times 4.184 rounded to 3 sig figs is 732. 732 times 15 rounded to 2 sig figs is going to be 11 times 10 to the 3, or 11 kilojoules in other words. Okay. The energy of the photon, so it's going to be Planck's constant times the frequency. The frequency is the speed of light over the wavelength. Speed of light divided by wavelength gives me frequency, because frequency times wavelength gives me speed of light for electromagnetic waves. Okay, so that's going to be 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8. That's going to be 1.986 times 10 to the negative 25. 1.986 times 10 to the negative 25 divided by 1.5 times 10 to the negative 6. Rounding to 2 sig figs is 1.3 times 10 to the negative 19 joules. Times 10 to the negative 19 joules. So then the number of photons, the number of photons needed, is going to be equal to, let's see, we have 11 kilojoules worth of photons that we're trying to get. So 11 kilojoules, we know that there's 1,000 joules in every 1 kilojoule. And we know that every 1.3 times 10 to the negative 19 joules is equal to 1 photon. So approximately how many photons is that? So 11,000 divided by 1.3 times 10 to the negative 19 gives us 8.5 times 10 to the 22. 8.5 times 10 to the 22 photons. And there we go, that was problem 10. Let's see, problem 11 says one of the radiographic devices in a dentist's office emits an X-ray of wavelength 2.09 times 10 to the negative 11 meters. What is the energy in joules and frequency of this X-ray? We've already done this. So you have the wavelength, use the speed of light divided by wavelength to get frequency, multiply frequency by Planck's constant to get the energy in joules, and that's it. Been there, done that. Number 12, the eyes of certain reptiles pass a single visual signal to the brain when the visual receptors are struck by photons of wavelength of 850 nanometers. If a total energy of 3.15 times 10 to the negative 14 joules is required to trip the signal, what is the minimum number of photons that must strike the receptor? Okay, so this is similar to what we just did, but no harm in doing it. So we've got the total energy of the photons. Total energy is 3.15 times 10 to the negative 14 joules. And let's see. They said the wavelength was 850 nanometers, so I'm going to take the total energy and then however many joules we have for every one photon. One photon is going to be X amount of joules, and we will figure that out. So wavelength is 850 nanometers, lambda is 850 times 10 to the negative 9 meters. Got to make sure to convert to meters before you find the frequency. And I'm going to treat that like it's 3 sig figs. So I'm going to include the 0 as a sig fig. But yeah, so HC over lambda, 6.626 times, hold on, I already did this calculation earlier. What's HC equal to again? It was 1.986 times 10 to the negative 25 times 10 to the negative 25, and then that divided by the wavelength, which is 850 times 10 to the negative 9, is 2.34 times 10 to the negative 19. So energy per photon, I'm getting 2.34 times 10 to the negative 19 joules per photon. So that's what I'll write over here. And let's see how many photons that is. .15. Whoops, wrong button. 3.15 times 10 to the negative 14 over 2.34 times 10 to the negative 19 gives us 1.35 times 10 to the 5 photons. 1.35 times 10 to the 5 photons. And by the way, for these questions, you can't have a fraction of a photon, but 1.35 times 10 to the 5 is not a fraction. It is a whole number. It's, what, 135,000, right? So that's an exact whole number of photons. That's allowed. You can't have 0.3 photons or anything like that. So whenever you encounter something like this, you probably won't end up having to round it all, but in the event where you might end up with fractions of photons, just round to the nearest whole photon. Just like how with money you would want to round to the nearest penny. But yeah, that was number 12. Let's see. Some Bohr model questions. Let's see, is there anything in here that we want to look at? 16, why is the electron in a Bohr hydrogen atom bound less tightly when it has a quantum number of 3 than when it has a quantum number of 1? Well, we haven't talked about the quantum numbers yet, but they're referring to the first quantum number, which is just the orbit number, or the energy level. So, as for the question of why the electron is less tightly bound in the third orbit versus the first orbit, it's because the force of attraction between opposite charges is stronger when there's a shorter distance between the attracting charges. The closer they are to each other, the stronger the attraction, or repulsion in the case of same charges. So that's 16. 17, what does it mean to say that the energy of the electrons in an atom is quantized? Yeah, so we talked about quantization, and since electrons can only have specific energies, the energies of electrons in their orbits around atoms are certainly quantized. There are only specific energy values that you can have. And you can't have, all real numbers as possible energies. Of course, the Bohr model fails in saying that you can't have energy levels between you can't have energies between specific energy levels, and the truth is you can, but they're still quantized. They're still specific sublevels within those energy levels, and we'll talk about those soon enough. Number 18, using the Bohr model, determine the energy in joules necessary to ionize a ground state hydrogen atom. Show your calculations. Okay, so to ionize means to completely remove the electron, so send it from whatever level it's at all the way to level infinity, which is, for all intents and purposes, outside the atom, even though technically you can consider an electron that's even at the far reaches of the universe to still be under some influence of the nucleus of an atom, even from that far away. It would just be a really, really, really small influence, so we treat it as being 0. But yeah, for that, if you just do, let me see, essentially what you'd want to do is just calculate the energy change as negative 2.18 times 10 to the negative 18. And then for your n final, just have infinity. So 1 over infinity squared. 1 over a really, really big number is approximately 0. Minus 1 over wherever it starts. So the ground state for hydrogen would be at n equals 1. So negative 2.18 times 10 to the negative 18 times the negative of 1 over 1 squared, which would still be 1, would give you exactly 2.18 times 10 to the negative 18. Hopefully that doesn't surprise anybody. That's how many joules you have to give an electron to kick it out of the atom. if it's in a hydrogen atom. In other atoms with other numbers of protons, you'll have to multiply that by z squared, and also you might have a different n depending on which level your electron is supposed to start out in. Okay, so that was 18. 19, the electron volt is a convenient unit of energy. We dealt with it earlier. It's the amount of energy that an electron gains when subjected to a potential of 1 volt. Okay, using the Bohr model, determine the energy in electron volts of the photon produced when an electron in a hydrogen atom moves from the orbit with n equals 5 to n equals 2. We've already done a transition for electrons. In fact, we've done 2 of them. So it's a been there, done that sort of thing. Only difference is you convert your final answer to electron volts rather than joules. Nothing too fancy there. Number 20, using the Bohr model, determine the lowest possible energy in joules for the electron in the lithium 2+ ion. So lithium 2+, that would be lithium minus all but one of its electrons. Lithium normally has 3 electrons, but it's lost 2 of them, so it's only got 1 electron surrounded by, or not surrounded by, but orbiting around 3 protons and a couple neutrons as well. Okay, let's do that one since we haven't really seen it. It shouldn't be too hard to do. So, of course, we would be in the first energy level. For lithium, we would be in the first orbit, and it would just be negative 2.18 times 10 to the negative 18 times z squared over n squared. Z for lithium is 3, so times 3 squared over n squared. That 1 electron is going to be in the first energy level, or first orbit. So 3 squared over 1 squared, and there you go. Nothing too complicated. The 3 and the 1 are exact numbers. Negative 2.18 times 10 to the negative 18 times 9 is negative 1.96 times 10 to the negative 17. We still keep 3 sig figs. And that's going to be in joules. All right. And there you go. That wasn't particularly hard. But the fact that they had to remove all but 1 electron is another problem that Bohr didn't deal with, which maybe we should talk about a little bit. So Bohr's model doesn't just fail for failing to explain some of those double lines that would require sub-levels between levels, or within levels, I should say. But Bohr's model also fails because it doesn't consider the influence of having other electrons. Bohr's model also fails with anything other than the hydrogen atom because it doesn't consider the influence of having multiple electrons. If you've got, a couple of protons here, like in the case of lithium, lithium can have 2 electrons in its first orbit and would normally have 1 electron in its second orbit, like so. But yeah, you have to consider the potential energy that this electron has due to not just being in the vicinity of these protons, but also being in the vicinity of other electrons. It's more of a concern for physics students rather than chemistry students, but that is another thing that Bohr failed to account for. So in the example we were given, they had to remove 2 of the electrons so that we could only focus on the 1 electron and not have to worry about the influence of having additional electrons. So that's why we worked with the lithium 2+ ion in that last example. Okay, some more Bohr questions here. Is there anything specific that I want to highlight? 20 we just did, 21 is similar. 22, using the Bohr model, determine the energy of an electron with n equals 6 in a hydrogen atom. Been there, done that. Negative 2.18 times 10 to the negative 18 times 1 over 6 squared, and you're done. 23, same thing, but it's 1 over 8 squared. 24, how far from the nucleus in angstroms, there's that word again, an angstrom is 10 to the negative 10 meters, or a tenth of a nanometer. How far from the nucleus in angstroms is the electron in a hydrogen atom if it has an energy of negative 8.72 times 10 to the negative 20 joules? Okay, that's also a physics question. Bohr did come up with an equation that allows you to calculate exactly at what distance these electron orbits are supposed to be at. But we don't need that for chemistry. That's a physics thing. If you are curious, look up something called the Bohr radius. Okay, 25. Again, that's another Bohr radius problem. 26, using the Bohr model, determine the energy in joules of the photon produced with an electron in a helium ion. Okay, been there, done that. Well, actually not quite. Okay, not quite. We've done parts of it. Okay, let's do 26. Let's do number 26. So it says, using the Bohr model, determine the energy in joules of the photon produced when an electron in a helium+ ion moves from the orbit with n equals 5 to n equals 2. And this marker's as good as dead. Say goodbye to Peach. To the trash you go. And the replacement for Peach will be... what should I use as a replacement? I think I'll go with orange. All right. So, where were we? Right, so we've got a transition from n equals 5 to n equals 2. Whoops, n, not m, to n equals 2. And it's for the helium+ ion. So helium with just one electron, essentially. Okay, so we just use the change in energy equation, except this time we have to multiply by z squared. Z squared is not equal to 1. That's the case for hydrogen. For helium, z is equal to 2, so z squared is 4. Negative 2.18 times 10 to the negative 18 times 1 over the final squared, so that's 1 over 2 squared, minus 1 over the initial squared, and then times z squared, which in this case for helium is 2, so 2 squared. Okay, so if we do this, then what do we end up with? All this stuff is exact numbers here, so I should be able to just plug all this into my calculator in one go. Negative 2.18 times 10 to the negative 18 times parentheses 1 over 4 minus 1 over 25 times 2 squared, which is 4. And I can see that the fan is dead set on interfering with my lesson. Negative 1.83 times 10 to the negative 18. Negative 1.83 times 10 to the negative 18 joules. The fact that the energy change is negative tells us that the electron lost energy overall, which makes sense because it's jumping down from a high orbit to a lower orbit. And so if it's losing energy, it emitted a photon, it did not absorb a photon. Photon was emitted, not absorbed. Okay. Anything else they asked about that one? No, they just wanted the energy in joules, and we're done. If you want to take the absolute value of this and calculate the frequency and wavelength of the corresponding photon, you're more than welcome to do so. I'm just going to move on. Let's see what we have next. 27 is the same as 26, but with lithium, so Z is equal to 3. Lithium has 3 protons after all, so more of the same, except you'd multiply in the end by 9 instead of 4 like we did in the previous problem. 28, consider a large number of hydrogen atoms with electrons randomly distributed in the n equals 1, 2, 3, and 4 orbits. How many different wavelengths of light are emitted by these atoms as the electrons fall into lower energy orbits? Okay, so this is just a matter of tallying. So you can go from 4 to 3, 4 to 2, 4 to 1, that's 3. You can go from 3 to 2 and 3 to 1, so that's a total of 5 so far. And you can go down from 2 to 1, that's 6. So 6 possible transitions can be made in the downward direction. And of course, if we're talking about absorption, you can also have 6 more transitions in the upward direction. Part B, calculate the lowest and highest energies of light produced by the transition described in Part A. So you would want to look for the biggest transition and the smallest transition. The biggest transition is going to be from 4 to 1, and the smallest transition is going to be from 4 to 3. Remember that the energy levels get closer to each other when you get into the higher orbits. Let me pull up that image again, wherever it was. Where was it? Yeah, this one. Yeah, so notice how energy level 3 is closer to 4 than it is to 2. The green line is closer to yellow than it is to blue. Energy level 4 is closer to 5 than it is to 3, and so on and so forth. Okay, so that's part B. Just do the calculation for 4 to 1 and 4 to 3, and there's your highest and lowest possible energy changes. Part C, calculate the frequencies and wavelengths from Part B. We'll skip that because we've already done it. Number 29, how are the Bohr model and the Rutherford model of the atom similar, and how are they different? We already answered this, but just to reiterate, the Bohr model and the Rutherford model both have the concept of orbits, except that the Bohr model only allows for specific orbits with specific energies and does not allow electrons to have any energies in between those. Whereas the Rutherford model assumes that the energy of an electron is continuous, the Bohr model treats the energy of an electron as being quantized. Only specific energies, you can't have all the values in between. Okay, so that's that. Is there anything else I want to do in here before I start talking about the quantum model? No, I don't think so. Okay, let's start talking quantum. What do I have lined up next? Let's see. Okay, not getting into quantum quite yet. There are still a couple of things we need to talk about which lead up to quantum. So a couple of additional things that, as far as chemistry is concerned, they're just things to kind of check off your list. You definitely learn about these things in a little more detail in physics rather than in chemistry, but let's just check these off our list. So we notice, or scientists noticed, that not only does light have particle-like behavior, which is what we see when which is what we saw with line spectra, essentially. The fact that light can act as discrete packets known as photons rather than just one big continuous stream, that gives light some very, very particle-like properties. And so somebody by the name of Louis de Broglie suggested that maybe the reverse is also true. Maybe it's not that light is particularly special in that it can behave both like a wave and like a particle, but maybe everything has both a combination has both wave-like and particle-like properties. So de Broglie basically said that the wave-particle duality of light extends to all things. Well, all things that move. So de Broglie figured that physical objects can have a wavelength and a frequency. So as for the wavelength, he came up with the following equation. He said wavelength, and sometimes we call this lambda sub d, the de Broglie wavelength, is equal to Planck's constant divided by the object's momentum. So momentum is simply mass times speed, or more precisely mass times velocity if you take direction into account, but this is not a physics class. So for big objects like you and me and cars and trucks, because the mass is so large even at modest speeds, your momentum is going to be really high. Planck's constant is already a really small number. It's 6.626 times 10 to the negative 34. So if you then divide it by a fairly large number, what will be a fairly large number for big objects like cars, then you're going to get a really, really small wavelength. In fact, a wavelength so small that it's not possible to observe it in the real world, and that's why we don't see cars doing the things that waves do. We don't see them phasing through other cars and doing constructive or destructive interference. Not that those terms would make any sense to you if you don't know your physics. We don't see cars refracting or diffracting the way that light and sound would. And it's because their wave behavior would require a wavelength that can't be observed. But on the other hand, if we think of really small particles like electrons, for really small particles with electrons that have really small masses, I believe the mass of the electron, if I'm not mistaken, actually, why even guess? My book's in front of me. I think it's 9.11 times 10 to the negative 31, but let's double check. Yes, it's 9.11 times 10 to the negative 31 kilograms. Times 10 to the negative 31 kilograms. And yes, the mass in this equation has to be in kilograms. Must be in kilograms. And this must be in meters per second for the speed. But anyway. So the mass of the electron is rather small. So an electron, even if moving pretty fast. I mean, it can't move faster than light. So even when moving pretty fast, an electron will actually have an observable wavelength, and that's why electrons actually display some wave-like behavior. If you don't know your physics, what you're about to see may not make a whole lot of sense to you, but it's the best I can do to help illustrate some of the wave-like behavior that electrons demonstrate. Let's go ahead and take a look first at what light can do when you run it through what we often call a double-slit experiment. So this is yet another PhET simulation that you can look up on Google and play around with if you really want to. I would have done the animated version, but I tried a test recording earlier, and for some reason my computer just can't handle it. I'm gonna need to get a new, better computer soon. This computer wasn't really built for recording video in the first place. But I digress. So what you have here is a bunch of, in this case, orange waves of light that are being sent from this wave generator on the left. They're being sent to the right, and they encounter two little slits, two openings in a barrier. And when they encounter those two slits, they basically act like a new wave source that just starts emitting waves in a sort of circular pattern outward from those holes. And so the wave from one hole can overlap with the wave from another hole, and they can interfere with each other. They can cancel each other out in some places and add up in other places. And what you see at the far right end of that is a black screen where you see a bunch of colored bars. You see a bunch of colored bars. So you see a black bar and an orange bar and a black bar and an orange bar. Those are called dark and bright fringes, respectively. And yeah, that's a thing that light can do. That's a thing that light can do when it interferes with itself, when two copies of the same light interfere with each other. Now, it turns out that electrons, even though they are technically particles, also demonstrate this wave-like behavior. In fact, let me dig up that image. Here we go. So electrons also seem to adopt similar behavior. If you look at the images on the bottom specifically, if you fire electrons in sort of the same way that I was sending off those beams of orange light in the previous slide, then even if you send them in one at a time through the double slits, even though they can only technically go through one slit at a time, somehow they know that other electrons will be coming in through the other slit, and they just know to kind of interfere with themselves ahead of time. And yeah, that weirds a lot of people out. They say that if you think quantum mechanics makes sense, then you don't really understand it. I think that might have been a quote from Niels Bohr, but I'll have to double check and confirm. So for now, don't take my word for it. But yeah, if you look at those black screens, eventually what you see happening is the electrons, at first there doesn't seem to be any pattern. They seem to just scatter about randomly. Then you get to the that next black screen, and you see that the electrons are actively avoiding certain strips on the screen, and then you let more time pass and you fire more electrons, and you find a very clear pattern of lines that the electrons seem to be aiming for. So there you go. There's electrons behaving like waves. Everything has a dual nature. Okay, so that was de Broglie's contribution to quantum mechanics. Of course, there's more to it than that, but again, it's more of a physics thing than a chemistry thing, so not going to get too bogged down by the details. Another contributor to quantum mechanics was a fellow by the name of Heisenberg. Was it Werner Heisenberg, I think? So Heisenberg introduced us to the uncertainty principle. Heisenberg's uncertainty principle. And what the uncertainty principle said was that you cannot precisely know both the position and the momentum of a particle, specifically regarding electrons and atoms. You can't precisely get their position and their momentum at the same time. The more precisely you measure one of them, the less precisely you measure the other. So the error margin in position, we can call that delta x. The error margin in calculating the momentum, we can call that delta p. And essentially, the inequality that Heisenberg gave us is that the margin of error for the position times the margin of error for the momentum has to be greater than or equal to Planck's constant over 4 pi. And remember, Planck's constant is a really small number, so I guess if we were to do a sample calculation, well, no, not even going to bother with a sample calculation. Let's just rearrange this a little bit. So let's say I measure the position of an electron very accurately, and my margin of error is on the order of, let's see. My margin of error is on the order of, let's say, 10 to the negative 12 meters. So let's say delta x is on the order of 10 to the negative 12 meters, on the order of picometers, if I'm not mistaken. Then I can say that the margin of error in my momentum has to be greater than or equal to Planck's constant over 4 pi, that part is just going to be a fixed amount, of course, times 1 over delta x. Now, delta x being really small, being 10 to the negative 12, means that I'm measuring my position very precisely. If I'm off by no more than 10 to the negative 12 meters, that's a pretty precise measurement of position. But if precise means that this has to be small, then if I'm multiplying by 1 over a small number, then all of a sudden this number is actually going to grow bigger. If I multiply it by something on the order of 10 to the negative 12, then it's going to become 12 orders of magnitude bigger. So all of a sudden you have a larger uncertainty, a larger margin of error in calculating the momentum of your electron. I hope that made some semblance of sense. Basically, the smaller one of these numbers are, the bigger the other one has to be, because at the end of the day, they have to be at least h over 4 pi. But yeah, there is a limit to how well you can learn everything there is to learn about a particular electron. Or, I guess, particles in general. I wouldn't worry too much about it if you're just doing chemistry. If you're doing physics, yeah, you might have to do a couple calculations with this. But that's Heisenberg's uncertainty principle. The more you know about one, the less you know about the other, and it has to do in part with the measuring techniques. The way you measure the position of an electron would necessarily screw up its momentum so that you wouldn't be able to calculate it as precisely, and vice versa. Okay, so that's de Broglie and Heisenberg out of the way. Now we introduce Schrödinger. So Schrödinger was able to come up with an equation known as the wave equation, which requires some advanced calculus to solve, so we're not digging into the equation, but Schrödinger gave us the wave equation, or the wave function, which he called psi, and I guess some people pronounce this epsi. It looks like a trident, Greek letter psi, psi, not pounds per square inch, for those of you who still even remember that unit from the gas laws video. No, this is the Greek letter psi, or some people pronounce it epsi or psi. I'm not sure, I just call it psi. And I guess I didn't really write it very well. Let me try that again. So it should look, yeah, like a trident. There we go. So Schrödinger came up with some fancy calculus formula that basically allowed us to calculate the probability of where an electron could be at any given time. Schrödinger basically took the wave behavior of electrons to another level and decided to, introduce probability into the mix. And so what he ended up coming up with, his calculations led to some predictions that you couldn't get from the Bohr model. So his equations predicted the existence of what are called orbitals. And these orbitals basically functioned as not the sublevels per se, but the components of the sublevels that Bohr was not able to find a proper explanation for. But there were other things that the Schrödinger equation accounted for as well. In fact, the Schrödinger equation involved a number of quantum numbers. If you take some advanced physics courses, you will learn about, I think it was 7 quantum numbers, but as far as chemistry is concerned, we're only going to focus on 4 of them. But before I get into those, let's talk about how probability relates to finding electrons in atoms. So let me see where my visual was. I know it's in there somewhere. No, not that, not that. Ah, here we go. So Schrödinger's calculations allowed us to come up with a bunch of different orbitals, the first of which is known as the s orbital. It has a spherical shape, and over there in the top you see the s orbitals associated with the first 3 energy levels. So there's the first s orbital is that small blue sphere, the second s orbital is both that red sphere and that blue sphere minus a slight gap in between the 2 spheres, and then the s orbital of the third energy level is 3 spheres in sequence, and again minus the slight gaps between successive spheres. So if you look down below each one, what you see is a series of graphs. Those graphs basically are probability density graphs. So if you want to find the probability that an electron will be located between, let's say, 0 picometers and 12 picometers from the nucleus, then you would basically calculate the area under the curve from 0 to 12, and that would give you the percentage chance that an electron could be found there at any given moment. And then if we look at the second and third graphs, they're pretty similar, except you have extra humps. And you notice that there are actually places between those peaks, between those humps, where the probability of finding an electron is 0. Those places are called nodes. So those are basically like the hollowed out spaces between successive spheres. Sometimes we also call them radial nodes. But yeah, so Schrödinger basically said, no, the electron can be anywhere and everywhere at any given time, but with different probabilities. There's some probability that it's right next to the nucleus. There's some probability that it's actually at the end of the universe. It's a small probability, but it's not 0. And it's most probable at any given moment that the electron is at one of those peaks that you see in the graphs. So that's how probability plays into it. The less you think about it, the more sense it will make. If you're not a math enthusiast and you're not a physics enthusiast, I wouldn't think too hard about this. If you're here for the chemistry only, don't worry too much about this stuff. But just know that, yeah, the probabilities seem to behave like a wave that seems to grow the further outward you go, but still goes up and down over time. And I guess in this case over distance. Okay, so there you go. There's the concept of probability introduced to modeling the atom. So, since the probability seems to wave, Schrödinger proposed a fix to Bohr's model of the atom, which can either be called the wave model or the quantum mechanical model. The wave or quantum mechanical model of the atom. So the quantum model of the atom introduces a bunch of what are called quantum numbers. And each of these quantum numbers describes something different about the properties of an electron. So the first quantum number is called the principal quantum number. I'll just abbreviate it QN, the principal QN. Maybe I should use a capital Q and capital N. The principal quantum number. So the principal quantum number is related to the average energy and average distance. Average energy and distance of an electron and by distance we mean distance from the nucleus. So the average energy and or distance of an electron is indicated by the principal quantum number. The principal quantum number tells you what energy level you're in. So in the quantum model of the atom, we call them energy levels. We don't call them orbits anymore. We call them energy levels. Or sometimes we call them shells. So the principal quantum number, the first quantum number, tells you what shell you're in. Shells or levels. Okay, the second quantum number, and I should probably give the labels for, well, not labels, but the symbols that we use to represent these quantum numbers. So the principal quantum number is called n, and it's not entirely different from the n that we've been using in the Bohr model. N equals 1 for the first shell, n equals 2 for the second shell, n equals 3 for the third shell, and so on and so forth. So nothing too different there, except, I guess, in the interpretation of what it means. We're no longer talking about fixed orbits, we're just talking about I guess you could say a most probable or average place where an electron can be and an average energy that it can have. Okay, number 2, the second quantum number, is called the azimuthal quantum number, and I've forgotten how to spell it. The azimuthal quantum number. Or more commonly known as the angular momentum quantum number. The angular momentum quantum number. And sometimes it's also just called the secondary quantum number. But yeah, the angular momentum quantum number, or azimuthal or secondary quantum number, is a description of the shape of space. It describes the shape of space. The shape of space an electron is likely to occupy. In other words, it tells you which sublevel you are in. In other words, it tells you which sublevel you're in, and we'll talk about this a little bit more in a bit. So there's your sublevels. The angular momentum quantum number is represented with the symbol L. The third quantum number that we're going to concern ourselves with, let me just draw lines between these. The third quantum number that we're going to concern ourselves with is the magnetic quantum number. Magnetic quantum number. Should have just stuck with the abbreviation. The magnetic quantum number tells us the orientation of the space an electron is likely to occupy. An electron is likely to occupy, and we'll elaborate more on what that means in a minute. And let's see, the magnetic quantum number is represented with the symbol m sub s. And do I have enough room for the fourth quantum number? The fourth quantum number, I'll try to fit it in here. The fourth quantum number, can you even read that? Tell you what, I'll write it up here since there's plenty of space. I'll write it up here. The fourth quantum number is the spin quantum number. Which tells us the direction of the magnetic field of an electron. So it turns out that electrons are able to generate a magnetic field supposedly by spinning, though you can't really confirm this because, well, electrons are spherically symmetrical, I would imagine. So how on earth could you tell if an electron was spinning? But then again, you could argue that it has to be spinning if you know your physics, because to generate a magnetic field, you'd have to generate an electric current, and to generate an electric current, charge has to move somehow around the center of the electron. So probably, but we can never say for sure, electrons spin around themselves. Let's see, so the direction of the magnetic field of an electron, and that's represented with the symbol m sub L. M sub L. Okay. So, let's see here. Oh, I should have added sublevels or subshells. So the second quantum number tells us about sublevels or subshells. Either term is correct, but I usually see the word subshell being used rather than sublevel, but they're both technically correct. Okay, so let's go ahead and dig into this. There's a lot of stuff to unpack here. So, first quantum number basically just tells you on average where your electron will be and what energy it will have, but it doesn't say specifically what the energy or location of the electron will be because, well, you don't know, you just know probability. And if you know the probabilities, at least you can find the average. The second quantum number tells you the shape of space. So, first quantum number, n, is going to have values starting from 1, then 2, then 3, then 4, and so on. So integers counting up from 1. The second quantum number, L, is going to have values that start counting up from 0. 1, 2, and so on. And the rule is that an electron has to have an angular momentum quantum number that is less than its principal quantum number. So for any given electron, L has to be less than n. So for example, in the first energy level, in the first shell, an electron is allowed to have an angular momentum of 0. It's not allowed to have an angular momentum of 1 or 2 or 3 because, well, it's in the first shell and it can only have L values less than its n values. On the other hand, an electron in the third shell would be able to have angular momentums of 0, 1, and 2. Or I should say angular momenta is the proper plural, but I digress. So if you're in shell number 3, you can be in subshells 0, 1, or 2. You cannot be in subshell 3. Less than, not less than or equal to. So L has to be less than N for any electron. Okay. Let me see. These L values correspond to different types of orbital shapes. So 0 corresponds to the s orbital, 1 corresponds to what's called a p orbital, 2 corresponds to what's called a d orbital, and I suppose I'll include 3 here. 3 corresponds to what's known as an f orbital, and if you go past that, you can have a G and an H, and an I and a J and a K and so on, for as many different orbital shapes as you need. Or I shouldn't say orbitals, but subshells. We're not quite at orbitals yet. So we already saw what S subshells looked like in that last figure we saw. S subshells have a spherical shape to them. P subshells, the typical P subshell, will have orbitals that have a dumbbell shape to them. So it looks like a pair of balloons that are tied together. That's the typical type of orbital you will find in the P subshell. In the D subshell, you'll typically find a double dumbbell. Imagine 4 balloons tied together at their ends. And of course, for the F subshell, the typical shape of space that you'll see being occupied by electrons is a quadruple dumbbell, which I don't think I even want to attempt to draw. I don't even know how to imagine if you had like 8 balloons all tied together, with each balloon basically touching the corner of a cube. I don't know how to show the 3D-ness of this, but no worries. I have some images that I'll show you later that'll be much more clear. Anyway, next up we've got the magnetic quantum numbers. So the magnetic quantum number has values that range from -L to L, from -L to +L, and they're supposed to be integer values. So I guess a better way of writing this would be to say that m sub L is an integer that's between -L and +L. So for example, let's say that I'm talking about a D subshell with L equals 2. Then for the D subshell, I can have ML is anything between -2 and +2. As long as it's an integer. So that would mean -2, -1, 0, 1, and 2. And these are basically labels for each of the different orientations that a d orbital can have. So a d orbital can have 5 different orientations. A p orbital can have 3 different orientations because it's from -1 to +1, so that's -1, 0, and 1. So p orbital can have 3 orientations, one where you've got one of these dumbbells lined up along the x-axis, one along the y-axis, and another one lined up along the z-axis. And in fact, I can show you what those look like right now. Let's go ahead and find... First off, you've got your s and p orbitals. So s orbitals only have one orientation. S orbitals correspond to an L value of 0. So the S subshell only has one kind of orbital, just one spherical shape. I mean, you can rotate it around and twist it and do whatever, but it's still the same old sphere. On the other hand, the P subshell has 3 different possible orientations for its orbital, or for its orbitals, I should say. So those 3 orbitals that you see together make up the P subshell. So P subshell is made of 3 orbitals, S subshell is made of 1 orbital. Next up we have, let me see if I can find it. Next up we've got the d orbitals. So all but one of the d orbitals have that double dumbbell shape that I talked about earlier. And yeah, those are the 5 different shapes of d orbitals you can have. That middle one definitely looks weird, and the reason it looks that way is because there's no reason why they actually have to have a shape that makes sense to us humans. In fact, these shapes are simply the result of solving Schrodinger's equations. So yeah, the math is messy, but the math says that these are the shapes that you would get. So 5 different shapes or orientations of d orbitals, all of which, by the way, are equal to each other in energy. So orbitals that fall within the same subshell, even if they have different orientations and maybe even slightly different shapes, or very different shapes if you consider what we have in the middle there, they still have the same amount of energy associated with their electrons, or the same amount of average energy, I should say. Okay, and then let's go to the f orbitals, which definitely don't all look like what I drew or even attempted to draw. So in fact, if you look at the 7 different f orbitals that you can have, you'll notice that only 2 of them fit that quadruple dumbbell shape that I talked about earlier. The second one and the second to last one are the only ones that are an actual quadruple dumbbell. All the other ones, 4 of them in fact, look like some weird, maybe you could call them triple dumbbells, 6-petaled flower shaped thingy. And then you've got the one in the middle, the 4th one, is it's kind of like that middle d orbital that we just saw, the dumbbell with donut rings around it. So yeah, you don't need to memorize all these different labels that you see underneath the orbitals. So you see the z cubed and the xz squared and the y times x squared minus z squared and all that stuff. You don't need to know what that means. That's for more advanced courses. And you also don't need to be able to draw the f orbitals or the d orbitals, but you will need to be able to draw the s and p orbitals, which shouldn't be too demanding. These are easy enough to do, so you shouldn't really have much trouble with them. Okay, so those are all the different types of orbitals that you can get within a given subshell. And some might be asking, well, what about going beyond f orbitals? What about g and h orbitals and so on? We don't really have atoms that use those orbitals, so until we do, when and if we do, that's when we'll be concerned with it. But for the time being, we'll just work with the 4 orbitals that we know electrons are occupying. But yeah, there you go. So that's the magnetic quantum number. Basically, each number represents a different orientation and therefore a different individual orbital within a subshell. So a subshell, actually let me work from the top. So a shell is made of one or more subshells. A subshell is made of one or more orbitals, and each orbital is going to have its own orientation, and each orbital can contain up to 2 electrons, because each electron in an orbital can have one of 2 different spin values. The electron spin can either be positive 1/2 or negative 1/2, plus or minus 1/2. And the plus 1/2 is indicative of a spin up, and the minus 1/2 is indicative of a spin down. What does that even mean? Let's take a look at another picture. So basically, depending on which way an electron quote-unquote spins, depending on the direction in which it spins, it will create a magnetic field in a specific direction. And when that electron is subjected to an external magnetic field, then it will either line up with the magnetic field perfectly, or the magnetic field will line up perfectly against it. And if it's lined up with the external magnetic field, then it will have lower energy than normal. If it's lined up against an external magnetic field, it'll have higher energy than normal. It's only a very slight difference, but that slight difference in energy between 2 electrons in the same orbital, in the same subshell, in the same shell, will have ever so slight differences in energy. Remember that thick yellow line in the line spectrum of sodium? Thick lines like that usually are a result of 2 lines being really, really close to each other, the difference between them being due to the slight difference in energy between oppositely spinning electrons. Of course, you don't always have an external magnetic field at play, but there is another reason why it would be a good idea to have electrons generating opposite spins, having 2 electrons with opposite spins within the same orbital, because if they've got opposite magnetic fields, then there's going to be a slight magnetic attraction between them, which definitely helps to minimize their energy. You see, if 2 electrons are going to occupy the same orbital, then they can repel each other because they both have negative charges. And to help reduce that repulsion a little bit and get the electrons into, a stable, what's the word I'm looking for? A stable pattern of movement, I guess. I'm not sure what the phrase is that I'm looking for, but in order to make sure that the electrons don't have too much energy and just kind of, end up flying all over the place and fly out of the atom and not stay put, generally speaking. They're always on the move, but oh my goodness, it's hard to put this into words, isn't it? But yeah, in order to add some stability to the electrons occupying the orbitals, having opposite spins definitely helps, because the less energy the electrons have, the more stability you can have. Stability generally comes from having the lowest energy you can possibly have. If you have a lot of energy, then you're going to try and do stuff with that energy. So once you're done expending your energy, once you're, you know, in a stable condition, you'll be at your lowest energy. You don't have any excess energy to spend doing random stuff that you may not be supposed to do. I don't know how much of that made sense, but yeah, we try to get as much stability for our electrons as possible. We try to keep their energy as low as possible in order to have stable atoms. Okay, so let me see here. What else do I need to say about these 4 quantum numbers before we move on to describing specific electrons? Let me think. Nothing is coming to me, but I guess I'll remember it later. Okay, so now we can move on to talking about what's known as an electron diagram. So electron diagrams are very helpful for helping us just kind of sort out where the electrons are within the atom, orbital-wise and energy-wise. Electron diagrams help us just kind of make a map, a mental map of where all the electrons are and what state they're in within an atom. So let's take an atom such as let's take an atom such as, let's do beryllium. Let's do beryllium. So beryllium is atomic number 4, and it's going to have 4 electrons. So beryllium has an atomic number of 4 and is going to have a total of 4 electrons. Its first 2 electrons, if we assume beryllium is in its ground state, and we assume the electrons are in their lowest possible energy states, then you can say that the first 2 electrons of beryllium are going to be inside the first s orbital. They're going to be inside the single s orbital within the only subshell, the s subshell of the first level. And what I would do is I would draw 2 arrows, one pointing up and one pointing down. The up and down represent the spins. They represent the electron spin. Next up, we've got 2 electrons that are going to be in the s subshell of the second energy level. The s subshell of the second shell, and we'd have those 2 electrons in there. So that's an electron diagram for beryllium. So there are a couple of rules for drawing these electron diagrams which I need to lay out. Let me show you this image over here that basically is like your boilerplate empty electron diagram. You fill this thing up with electrons starting from the bottom to the top. So if you read it from bottom to top, you first put electrons in the s subshell of the first energy level, then in the s subshell of the second energy level, then the p subshell of the second energy level, which you see has 3 bars to it. Those 3 bars represent the 3 different p orbitals. Each orbital can carry 2 electrons, one with a spin up and one with a spin down. Then, of course, after the second level p subshell, you go to the third level s subshell, then third level p. Then you don't go to the third level d subshell, you go to the fourth level s subshell first. There is a reason for this. There's actually a formula that you can use to determine which subshell you should go to first, but the reason that the subshells are filled this way is, like I said in the beginning, you fill from lowest energy first. So you try to put electrons in orbitals such that they have as little energy as possible. If you start filling from the top down, then you're drawing the electron diagram for an excited atom, and an excited atom or ion, I suppose. And that's not the typical state that atoms are in. Atoms are typically in their ground state. So, as for the reason why the orbitals fill in the order they do, as for what is it that determines the overall energy of an orbital, we have a formula which is basically just n plus L, a very, very simple calculation. N plus L tells you, or at least gives you a general sense of, the total energy an electron would have in a given orbital. So, for example, an electron in the 1s orbital, so n equals 1, and s corresponds to an L equals 0. Oh my, that's really bad. The ink just leaked through. Okay, as I was saying, so s corresponds to an L value of 0, so this corresponds to n equals 1. S corresponds to L equals 0. So I would do 1 plus 0, and of course I would get a total of 1, and that gives me an overall sense of the energy an electron would have in the 1s subshell, the s subshell of the first energy level. If I take a look at 2s and 2p and 3s and 3p, and let's see, in the third level you can also have d orbitals, and as for the reason why, again, it's this L has to be less than n rule. So as n gets bigger, the number of possible orbitals that you can have also increases. So you have s orbitals from the very beginning, p orbitals start showing up from level 2 onward, d orbitals start showing up from level 3 onward, f orbitals start showing up from level 4 onward. In case you were wondering about that, there is no 2D, there's a 3D, a 4D, a 5D, and so on. But no 2D, and similarly there is no 1P or 1D for the same reason. Okay, lost my train of thought. Oh, right, let's go ahead and calculate the n plus L values for each of these. So here I've got 2 plus 0, here I've got 2 plus 1, 3 plus 0, 3 plus 1, oh, and I forgot, let's list 4s as well, 3 plus 2, 4 plus 0, and I think that'll be enough. Okay, so let's see here. And then 1s was 1 plus 0. So 1s is the lowest of them all. 1 plus 0 is 1, and that's the only one that gets a 1. 2s gives you 2 plus 0 is 2. 2p gives you 2 plus 1 is 3. And 3s gives you 3 plus 0 is 3. Okay, so I know that 2s is going to come before 2p because 2 is less than 3. But 2p and 3s both give you a total of 3. So which one comes first? In the case of a tie, the tiebreaker is whichever one has the lower n value would be lower in energy. So 2 plus 1 versus 3 plus 0. 2 plus 1, the 2p orbital would get filled first because 2 is less than 3. So first you compare the n plus L values, then you compare the n values alone if there is a tie. Okay, 3 plus 1 gives us 4. 3 plus 2 gives us 5. 4 plus 0 gives us 4. Oh, so 4 plus 0 is 4. 4s gets filled before 3d. So this rule saying that you have to fill lowest energy subshells first is called the Aufbau principle. So that's one of the rules for drawing electron diagrams. You fill lowest energy subshells first, and to determine or compare the energies of subshells, you compare their n plus L values, and if they tie, you compare their n values. Or you can forget about all this and just memorize. You can just memorize instead the following pattern. So it goes S, S, PS, PS, DPS, DPS, FDPS. Can you even see that on the screen? Let me move the paper up. FDPS, FDP, and there would theoretically be an S here, except that by the time you get to this point, you don't have an atom currently discovered that has enough electrons that would require you to fill this s orbital. So in fact, it actually stops right there. So let's see, s orbitals start numbering off from the first shell onward. S has an L value of 0, which is less than 1, so you will find it in shell number 1 and every shell after that. So 1, 2, 3, 4, 5, 6, 7, and we're not going to get to the 8s level, so no need to worry about it. The P subshell starts showing up from the second shell onward. P has an L value of 1, which is not less than 1, but is less than 2, so you can find it in the second subshell, or sorry, in the second shell, and then every shell after. So 2, 3, 4, 5, 6, 7. D orbitals start showing up from the third shell onward. D has an L value of 2, not less than 2 or 1, but is less than 3, so you can find it in the third shell and in the fourth and fifth and so on. And finally, F orbitals, they start showing up from the fourth shell onward. The F subshell corresponds to an L of 3, which is not less than 3, 2, or 1, but is less than 4, and is less than 5. And there you go. So that's the ordering. So 1s, then 2s, then 2p, then 3s, then 3p, then 4s, and so on and so forth. So yeah, either remember this n plus L rule, which is what I would prefer you do, or memorize this. I mean, I have the pattern memorized, but I can also justify it because I know the n plus L. So what I really want you to do is both. What I really want you to do is both, and maybe take the time to just verify that this is indeed the correct pattern on the basis of the n plus L values. But yeah, that's the filling order of subshells. Okay, so that's the filling order of subshells. Now, the thing that I was trying to remember, and I just realized what it is now, we didn't talk about subshell capacity yet. We didn't talk about how many electrons can I have in a particular shell and how many electrons can I have in a particular subshell. How many electrons? Let's start with a subshell. How many electrons can we have in, let's say, the D subshell? It doesn't matter which shell it's in. The D subshell will always be comprised of how many orbitals? Well, the number of orbitals depends on the number of orientations you can have. So D corresponds to an L of 2. So you can have 5 orientations, -2, -1, 0, 1, and 2. So for each orientation you have an individual orbital. Each individual orbital can carry 2 electrons, one with a positive spin and one with a negative spin. So 5 orbitals, 2 electrons each. That's a maximum of 10 electrons. So you can have a maximum of 10 electrons. I'll just use E- as a symbol for electrons. But yeah, you can have a maximum of 10 electrons in the D subshell. What about the P subshell? What about the P subshell? The P subshell would have 3 orientations. P has an L value of 1, so you have M sub L will have values of -1, 0, and 1, or if you prefer, X, Y, and Z, the 3 orientations of the P orbital. And each one of those will be able to carry up to 2 electrons, so as a maximum, the whole P subshell can carry 6 electrons. Okay, so then now let me ask this. How many electrons can be carried by the third shell? How many electrons? How many electrons in the n equals 3 shell? You might remember from very close to the beginning of this video that I talked about how all the orbits have different capacities for the number of electrons that they can contain, and I said that the third orbit can carry 18 electrons. Let's see if that's true. So the third orbit, or rather the third shell as it's called in the quantum model, or the third energy level if you prefer, has how many different subshells? So with n equals 3, I can have L equals 0, I can have L equals 1, I can have L equals 2. I cannot have L equals 3. I cannot have L being greater or equal to n. Again, that rule right there, L has to be strictly less than n. So I can have the S, P, and D subshells. Well, the S subshell only has 1 orbital. From -0 to +0, there is only 1 integer, it's 0. So I've got a single S subshell, a single S orbital making up my S subshell. I've got 3 p orbitals making up my p subshell, and I've got 5 d orbitals making up my d subshell. So that's a total carrying capacity of 2 electrons per orbital is 2 times 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 2 is 18 electrons. So yeah, I can have up to 18 electrons. And there they are. Spin up and spin down, one of each for each individual orbital within each individual subshell within each individual shell. It's kind of like an addressing system. It's kind of like N is the street you're on, while L is the building you're in, while ML is the specific apartment within the building, and then MS is like the individual in the building, or in the apartment, assuming that the apartment only allows for up to 2 people to live there at a time. Let's say we're talking about 1-bedroom apartments here to make that more realistic. So yeah, the apartment building analogy is a very commonly used analogy for the 4 quantum numbers that we have here, and how they, identify specific electrons. But I think that this material is clear enough without the need for an analogy, but I could be wrong. Maybe some people need that analogy in their minds. Anyway, going back to electron diagrams then. So one of the rules for drawing electron diagrams is the Aufbau principle, but there are other rules as well. So let me move on to, Let me move on to the electron diagram for nitrogen so that we can explore something else. Actually, should I do nitrogen or oxygen? Let's do oxygen. Okay, so I'm going to try and draw the electron diagram for oxygen now. So Aufbau principle says to start with 1s, of course. Oxygen has atomic number 8, so assuming it's a neutral atom, we're just talking about 8 electrons. So you've got the 1s subshell, which is going to contain 2 electrons. The 2s subshell will contain 2 more of our electrons. Then we go to the 2p subshell. The 2p subshell has 3 orbitals. And how many electrons do I have left to put in here? So I've already used up 4 out of 8. So I've got 4 more electrons to put in here. But how exactly do I distribute those 4 electrons across these 3 orbitals? Should I put 2 electrons in here and 2 electrons in here and leave that 3rd orbital empty? Or should I put 2 and 1 and 1? Well, here we have another rule that we need to follow called Hund's rule. We have another rule to follow that's called Hund's rule, and it's actually rather intuitive. Once you practice it enough, you won't even need to remember the official statement of Hund's rule. You'll just kind of remember it through almost like muscle memory. You'll just have a feel for it, and your hands won't let you do it any other way. But Hund's rule basically says that you fill electrons into orbitals as singles first. You fill them as singles first, and you only pair the electrons up if you absolutely have to. You only pair the electrons up if you absolutely have to. So I can give each of these its own individual space, but then I have one last electron that I need to put in. All the spaces are already occupied, so somebody is going to have to share a room with somebody else. And there you go. That's how you should draw the electron diagram for oxygen. And by the way, it doesn't matter which of these 3 is the one that ends up holding the pair. I could have just as easily drawn this and put the 4th electron in there, and that would be fine. It doesn't matter which of the 3 contains the pair, but you have to fill them as singles first and then pair them up afterwards. Usually we draw these in a left to right fashion, so when we do have to pair things up, we just keep going left to right. Makes it easier to read and makes it easier for your teacher to grade. You don't want to give your teacher a hard time grading your papers. You can do fancy stuff like this on your own time, but you don't want to put this on a test just because you don't want to, take chances and have the teacher miss the fact that you drew your double arrow somewhere else, somewhere where your teacher doesn't expect to see it. I mean, if I was your teacher, I would notice it and give you full credit, but you never know. Some teachers can be unreasonable, some teachers have poor eyesight, all sorts of possible problems that could arise depending on who your teacher is. But yeah, that's Hund's rule. And there's actually one more rule that I've been following, which I guess we already justified it earlier when we talked about electron spin, but let's go ahead and state it explicitly. So there's something called the Pauli exclusion principle that also needs to be taken into account when drawing electron diagrams. The Pauli exclusion principle. Pauli exclusion principle. Which says the following. No two electrons in the same atom can have an identical set of quantum numbers. An identical set of quantum numbers. So, if we're talking about a single atom, no two electrons in that atom can be in the same shell, and also in the same subshell, and also in the same orbital, and also have the same spin. They have to be different on at least one of those four things. One of those four things has to be different for each electron. So when I have to put two electrons in the same specific orbital, so I guess this would be the -1 orbital. Let me label these -1, 0, and +1. If I have to put two electrons into the -1 orbital of the 2p subshell, then by definition they're going to have the same n value. They're both going to have n equals 2. They're both going to have the same L value. They're both within a p subshell, so they both have L equals 1. Both of these electrons have the same m sub L value of -1. And if they were both here, they'd both have 0, and if I put them both here, they'd both have +1. But yeah, so if they're in the same orbital, they have the same n, they have the same L, and they have the same m sub L. So your last line of defense against violating the Pauli exclusion principle is that you give them two different ms values. Ms can be positive or -1/2, so if one of them has a spin up, the other has to have a spin down. That's the only way that they're going to have different sets of quantum numbers. So, in other words, the Pauli exclusion principle says when you pair up electrons, make sure they have opposite spins. So, do not do this. Do not do this. This right here, not allowed. Do not have 2 electrons with a spin up. Do not have 2 electrons with a spin down. By the way, you don't have to have spin up as the first spin occupying an orbital, so you can draw this for the last subshell of oxygen, and this is fine too. But usually we start with up and then down because, I don't know, I guess it just has a nice flow to it, and it feels appropriate to start with positives before negatives. I don't know. It feels appropriate to start with up before down. When you think of directions, if I give you a sentence and I leave a blank open and I expect you to fill it with a direction, usually the word up pops up in your head before the word down does. People say up and down, they don't often say down and up. So yeah, but you can definitely start by having them down if you want to, and then add the up spin electrons when you have to pair them. It's not what most normal people do, but you're more than free to be weird. Just, again, be careful with your teacher. I think even the most unreasonable teacher in the world would still have to accept this and not notice any problems with it, versus this, where, again, a teacher could just miss that you had it in the second or third orbital rather than the first. But then again, there are some very unreasonable teachers out there, so who knows? My recommendation is just to play it safe, but know that it doesn't really violate the rules if you have spin down electrons before you put spin up electrons in your orbitals. Any other comments I would like to make on this? Well, I guess now we can get into bigger atoms with more electrons. And write electron configurations, but before that there is one more thing I'd like to talk about. So electron diagrams can be drawn like this, which is how I typically like to draw them, but I've also seen people draw electron diagrams using boxes and kind of orienting everything horizontally. So I'm going to rewrite the electron diagram for oxygen using that other method. So here's another method for drawing electron diagrams. You can have the 1s orbital, or 1s subshell, which is just made of one orbital. Then you've got the 2s subshell, which is also made of just a single orbital. Then the 2p subshell, which is made of 3 orbitals. Notice how I drew them. Singles first, then pair them up when you have to. If you get into the habit of drawing them that way, just get into the habit of filling in singles first and then going back, kind of like a typewriter. I guess most of you might not even know what a typewriter is given your age, but yeah, just fill the orbitals one electron at a time, then go back and pair things up if you still have electrons remaining to fill. So there you go. There's another way of drawing the electron diagram for oxygen. I've seen this in some textbooks, and I suppose it is better when you don't want to take up too much space on the page, but I definitely prefer the vertical way of doing things, because I didn't really draw it to scale here, but if you do draw it to scale, you can actually see like the difference in energies between subsequent subshells. At the very least, this verticalness helps give me a stronger sense of the energies are higher the higher up you go. But I digress. Now let's talk about electron configurations. Electron configurations. Electron configurations. Basically, an electron configuration is really just a summary of an electron diagram. So, if I wanted to write the electron configuration for oxygen in the ground state, then I would just write this. So I've got the 1s subshell, which has 2 electrons in it. The 2s subshell then has 2 electrons in it. Then the 2p subshell has a total of 4 electrons in it. And there you go. That's it. It's really that simple. So you just write down the principal quantum number and the subshell type, and then just the number of electrons in that subshell as a superscript, and you're as good as done. So what's great about this is that it's quick and easy and you don't have to worry about distributing arrows, but what's bad about it is, well, you don't get to see which electrons are paired and which ones are unpaired. So if I give you this and I don't tell you that it's oxygen, then you're still going to have to go back and do this, especially if I ask you how many unpaired electrons are there for an atom in the ground state that has this configuration. And then you'd have to go back to this, you'd have to go back to your electron diagram and notice that you have 2 unpaired electrons. But yeah, so that's electron configurations, really simple stuff, and they can get kind of nasty for bigger atoms with more electrons. So let's take a look at, say, the electron configuration for, let's say the electron configuration for something like chlorine. Electron configuration for something like chlorine. Chlorine has 17 electrons. So let's go ahead and see. So 1s2, 2s2, 2p6. So far that's 2 plus 2 plus 6 is 10 electrons used out of 17. After the 2p subshell is the 3s subshell, and I'm going to max that out with 2. That is 12 electrons so far, 5 remaining. And after 3s is 3p, and the p subshell can hold up to 6 electrons, so yeah, I can put 5 in there. And that's it. So that's 2 plus 2 plus 6 plus 2 plus 5 is 17 electrons. That's perfect. Now, imagine if I picked something else. Imagine if I picked bromine, which has even more electrons. Imagine how much longer this would get. So bromine has 35 electrons. Let's go ahead and figure out what its configuration would be. 1s2, 2s2, 2p6, 3s2, 3p6. You definitely have more than enough electrons to fill all those subshells. After 3p is 4s. I'm going to put 2 electrons in there. Then after 4s is 3d, and the d subshell can hold up to 10 electrons, and I'm going to fill it with 10 electrons, and I still won't have used all 35. Let's see, 2 plus 2 plus 6 is 10, 18, 20, 30. I still have 5 more to go. 3p, or wait, no, not 3p, 4p, 4p, 5. Okay, there we go. So, yeah, this is long and time consuming, and you also have to know your Aufbau principle and, you know, memorize which orbitals need to be filled first. So, this just feels like a very tedious, time-consuming process, but there is a shortcut you can take. There is a shortcut you can take. Let's take a look at the electron configuration for argon. Argon is a noble gas with 18 electrons. It's got 1 electron more than chlorine. So in fact, it's going to be just like chlorine in every way, except instead of a 3p5, it's going to end with a 3p6. So 1s2, 2s2, 2p6, 3s, whoops, 2p6, 3s2, 3p6. Okay, that's argon. Oh, but wait a minute. That's argon. So in fact, you can actually write bromine in a more condensed form. A more condensed electron configuration for bromine, you can just write in brackets argon, meaning fill up all of the subshells of argon in its ground state, and then 4s2, 3d10, 4p5. I've actually seen people also write this another way. So I see people that will actually write the 3d10 before the 4s2 and the 4p5, which, I mean, it isn't wrong, but yeah, be on the lookout for that. So some people will do it this way. These two are the same thing, but I would rather write it this way. Just following the order that is dictated by the Aufbau principle. Filling lowest energy orbitals first. This doesn't mean that they filled the 3D subshell and its orbitals first. It's just that they have different criteria for what's the word I'm looking for? They have different criteria for how they order these. They order them based on N and then L. So lowest N's first, then for ties they go with lowest L's, and you know, I guess that's fine, but again, it's not for me. This is the more traditional way of doing it, but you will see textbooks that do it this way too. So don't freak out if you see it. But be ready to tell the author of the textbook that they're wrong and start a pointless argument over it. Okay, so we can definitely use noble gases to simplify the process, because every noble gas, whether it's helium or neon or argon or whatever, every noble gas has an electron configuration that's always a bunch of completely filled subshells. So that's why noble gases are particularly useful for abbreviating or condensing these what do you call them? Electron configurations. Now, if I write down the condensed electron configuration for chlorine, if you work out the electron configuration for neon, you will find that it's 1s2, 2s2, 2p6. Neon is atomic number 10. It has 10 electrons. So chlorine, I can write as neon, and then 3s2, 3p5. And you might notice something between chlorine and bromine. They both end with a p5. Their electron configurations both end with a p5. In fact, all of the atoms in the 17th column of the periodic table are going to end with p5s. And all of the noble gases, which are in the 18th column of the periodic table, are going to end with p6s. There's actually a relationship between orbital filling and the structure of the periodic table. Now the shape of the periodic table makes even more sense than it ever did before. So if you look at that diagram I have up on screen, you can now look at the periodic table as being composed of a bunch of blocks. The S block, the P block, the D block, and the F block. So the S block, I can't talk today. The S block is basically the first two columns of the periodic table, and also helium, which is shoved over to the far right side. Helium is technically part of the S block. The P block is the far right end of the periodic table. The D block is the central block of the periodic table. It's a bunch of transition metals, and then of course you've got the F block is the two rows that you have pulled kind of outside and below the periodic table. And you'll notice that the widths of those blocks correspond to the electron capacity of the S, P, D, and F subshells respectively. The S block is 2 columns. S orbitals, or I should say S subshells, which are really just made of 1 S orbital each, can carry up to 2 electrons, so 2 columns. The P block, you've got 6 columns, and the P subshell has 3 P orbitals, which can carry a total of 6 electrons. The D block with 5 orbitals in the D subshell, you can carry up to 10 electrons, so your D block is 10 columns wide. And then your F block down at the bottom, F orbitals can have 7 different orientations, as we saw. 2 electrons per orbital, so 14 total electrons, 14 columns for your F block. So in fact, you can actually read electron configurations off of the periodic table. You can actually read electron configurations off of the periodic table if you start looking at the periodic table in terms of S, P, D, and F blocks. For example, let's say I wanted to get the electron configuration of, oh, I don't know, let's do phosphorus, for example. If I want to do phosphorus, I just kind of start going through the periodic table row by row. So I've got the, let me put a marker over here so that the fan doesn't blow this thing over. So I start from here and I go left to right. So I've got 1s2. In fact, I can even skip that. I can just start with the most recent noble gas. right? I can use a condensed configuration. So the last noble gas that came before aluminum was neon. So I start neon, and then 3s2, 3p1. There you go. Aluminum is neon, then 3s2, 3p1. Aluminum is neon, 3s2, 3p1. It's really that simple. However, this will fail you in a couple of cases. So let's talk about those cases. Let's talk about the electron configurations of a couple of specific transition metals. The first one I want to call your attention to is chromium. So what's the electron configuration for chromium? You would think, judging by its location on the periodic table, 24 electrons, so you would think it would be, let's see, argon, and then 4s2, 3d4. That's what you would think. You would think that chromium is argon, then 4s2, then 3d4. But you would be wrong. In chemistry, you have patterns with exceptions. You do not have rules. Experimental data suggests that the correct electron configuration for chromium in the ground state is actually argon 4s1 3d5. Why? Well, some people argue that it's because unpaired electrons, having a bunch of unpaired electrons in a single subshell is somehow more stable, but that's not really much of an argument. Let's look at the electron diagrams for both of these and see if we can explain some stuff. I'm not going to draw the full electron diagram starting from 1s, but you know. So let's have our 4s2 and 3d4. So the d subshell again contains 5 d orbitals, all equal to each other in energy. I don't remember if I said this earlier, but I should have. So all the orbitals within a particular subshell are said to be degenerate orbitals. And degenerate in chemistry, specifically in the quantum mechanical sense, means having equal energy. Degenerate orbitals are orbitals of the same energy, therefore orbitals that are in the same subshell. Degenerate orbitals, orbitals with the same energy. That's just a vocab word I forgot to mention earlier. Orbitals with equal energies. And again, it's not actually the orbitals themselves that have the energy, but the energy of an orbital specifically refers to the energies of the electrons in those orbitals. But yeah, that's what degenerate orbitals means, not the typical definition of degenerate that you see in arguments between people online, calling each other a bunch of degenerates or whatever. Not that kind of degenerate. Anyway, back to this. So 4s2 3d4 looks like this. And 4s1 3d5 would look like this. Let's do it in a different color so it's easier to see. And maybe draw the 4s a little lower so that I have enough space to write 3d. Whoops, what did I do? No, 4s1 3d5. So some chemistry teachers will tell you that, you know, this is happening because having five unpaired electrons here, having this sort of symmetry is somehow magically more stable than this this less symmetric looking diagram, but there's absolutely no truth to that. There's nothing special about having 5 singles versus 4 singles and a double, except one thing, which is that 4s and 3d are very close to each other in energy. 4s and 3d are very close to each other in energy. So if you have to choose between pairing up 2 electrons in the 4s versus simply adding 1 electron into an otherwise unoccupied orbital in the 3d, I would guess, energy-wise, this makes more sense if the energy of the electron when paired in the 4s is less than its energy when unpaired in the 3d. So I'll just make up numbers here, but let's say the 4s is at an energy of, I don't know, 12, and let's say 3d is at an energy of 14. And you can say they're 12 and 14 joules or electron volts or whatever you want, I don't care. But for the sake of this example, let's just use 12 and 14 as numbers to give us a concrete sense of what's going on. So default energy of an electron in the 4s is 12 units of energy, whatever units they are, and default energy of electrons in the 3d orbitals will be 14. But pairing the electrons comes with an additional cost. When 2 electrons are paired in the same orbital, that's going to cost more energy. So the first electron gets in, it costs it has 12 units of energy, but when you pair up another electron with it, let's say that the effect of pairing adds like a +3 energy tax. Let's say that pairing increases the energy by 3. +3 for pairing. Well then, in that case, if I take my last electron and pair it in the 4s orbital, like what I have over here, then based on the made-up numbers that I have, that would mean that that electron would have an energy of 15 and not 12, versus if you just put it into this unoccupied space in the d orbitals, you would just have an energy of 14 rather than 15, and if you have to choose between 14 and 15, 14 is better. So you don't really need to fully understand that explanation. If you don't care for it, you won't really need to know it, but for those of you who do care, I hope that was helpful. I hope that made some sense, even if the numbers I used to illustrate the idea were quite arbitrary. But yeah, sometimes you have these exceptions, and the only way to find these exceptions is to just do your experiments in the lab and figure out what's going on. Just record your results and figure out what the configurations are. But for most atoms you will encounter, you won't see this problem. You will see this for a couple of atoms specifically, so it's a good idea to memorize those. Chromium, molybdenum, copper, and silver. Chromium, molybdenum, copper, and silver. I think gold might also be included in there, but I'm not sure. And I don't know if tungsten is also included in there. But for chromium, molybdenum, copper, and silver at the very least, just remember that chromium and molybdenum do not end with S2D4, but rather they end with S1D5. So that's chromium and molybdenum. Copper and silver are similar cases, except for copper and silver, you would think, based on their position in the periodic table, that they end with S2D9, and instead they end with S1D10. Copper and silver end with S1D10, not S2D9. So those are just a couple of exceptions that you're going to want to keep in mind. Some teachers call this the D4 and D9 rules, but there's nothing that's inherently, I don't know, rule-worthy about having a D4 or a D9. So it's not really a rule. It's just, you know, it's a couple of exceptions to a general pattern. So there you go. Those are some exceptional cases for electron diagrams and their corresponding electron configurations. Let me think here. What was I going to say? Let me look at my notes. I don't think there's much left to talk about here. Ah, yes. Okay, so with this I think we'll be able to wrap up. We just need to talk a little bit about ions and talk about valence versus core electrons. So first let's talk valence versus core electrons. Valence versus core electrons. You're going to want to remember this for the next video. You're going to want to remember especially what valence electrons are. Valence versus core electrons. Okay, so basically, whenever you write the electron configuration for an atom that has lots of electrons, such as bromine, let me go ahead and rewrite that one. If I take a look at bromine, its configuration is going to be argon, followed by, let's see, that's going to be 4s2, 3d10, 4p5. If we look at this configuration, we can easily identify what the outermost electrons of bromine are. The outermost electrons of bromine you can tell just by looking at the N values. The 4s and the 4p have an N value of 4, so these electrons are in the fourth shell. They're in the fourth orbit, so to speak, if you go back to the Bohr and Rutherford models. So these are the outermost electrons. These are the electrons that are most exposed. They're on the outside of the atom, they're the ones that are going to be gained or lost whenever ions are formed. So these are called the valence electrons. The outermost electrons are called valence electrons. The outermost electrons are called the valence electrons. And the outermost shell, basically the highest n value, tells you what your valence shell is. So in the case of bromine, the valence shell is the 4th shell. In the case of chlorine, the valence shell would be the 3rd shell. So chlorine would be neon 3s2 3p5. So for neon, the valence shell is the 3rd shell, and all the electrons in the 3rd shell are the valence electrons of, did I say neon? Chlorine. The valence shell is the 3rd shell for chlorine, and chlorine's valence electrons are the 7 electrons that are in its 3rd shell, 2 of which are in the s subshell, 5 of which are in the p subshell. So yeah, chlorine and bromine have the same number of valence electrons, and that should make sense. The periodic table is structured in such a way that atoms in the same column will typically have the same number of valence electrons. It'll be a little bit different for transition metals sometimes. But outside of the transition metals, the number of valence electrons of atoms in the same column in the periodic table will be identical. They'll have identical numbers of valence electrons. All other electrons beside the valence electrons are called core electrons. So core electrons, all non-valence electrons. So loss or gain of electrons happens at the valence shell level. Always happens to the outermost electrons, and of course, once you start losing electrons, you lose them from the highest energy valence subshell first, and then the next highest, and then the next highest, and so on. When gaining electrons, it's pretty much the same as just writing the electron configuration for an atom with more electrons. So for the chloride or bromide ions, if I wanted to write the electron configurations for either of those, it would be really simple. The electron configuration for the chloride ion is the same as the electron configuration for argon. It would be neon, and then 3s2, and then 3p6, right? The negative charge means I have one more electron than normal, and this is the same as the configuration for argon. For bromine, it's going to have the same configuration as krypton. So it's going to be argon, and then 4s2, then 3d10, then 4p6, which just so happens to be the configuration of the noble gas krypton as well. So when adding electrons, when making anions, nothing much changes except you increase the total number of electrons that you have to fill into your orbitals. With cations, it's a bit of a different story. With cations, it's very easy to fall into a certain trap, a trap that one sets for themselves, but a trap nonetheless. So if I were to look at, say, what do I want to do? Let's say sodium ion. You could say, well, sodium ion is sodium minus 1 electron, so that's the same as neon, right? Well, yeah, in this case you can get away with it. So it's going to be 1s2, 2s2, not 3, 2p6, and that's it. Normal sodium is just 1s2, 2s2, 2p6, 3s1, and of course neon is 1s2, 2s2, 2p6. So for sodium it works if you just think of sodium minus 1 electron as being the same number of electrons as neon, therefore it has the same electron configuration as neon. You can tell that to yourself, and in the case of sodium ion you'd be right. In the case of non-transition metals you'd be fine. But that's not really how you're supposed to do it. You're really supposed to start with the neutral atom and start taking electrons away from the valence shell. So take away the 3s electron to get the sodium ion. This is especially important for transition metals because let's take a look at let's take a look at, what do I want to pick? Let's say I pick titanium. Let's say I pick the titanium 2 ion. Titanium 2. If you look at the periodic table, titanium has atomic number 22, so the titanium 2 ion would have 20 electrons. So if you try to treat it like calcium, which has 20 electrons, then you're gonna mistakenly write this for titanium 2. So calcium would be argon followed by 4s2. But titanium 2 is not argon 4s2. Titanium 2 is, well, let's start with just plain old titanium first. So plain old titanium is going to be argon 4s2 3d2. Now, if you write the electron configuration for titanium 2 as 4s as just argon 4s2, then what you're essentially saying is that when you removed the electrons from titanium, you removed them from the 3d subshell, which doesn't make sense because the 3d subshell is deeper inside the atom than the 4s subshell is. The higher the n value, the farther away from the atom you are, and only the farthest away electrons are the ones that will get plucked off the most easily. So in fact, you have to subtract from the valence electrons. The outermost electrons are at level 4, not level 3. So subtract 2 electrons from there, and you have argon 3d2, and some people will even write this as argon 4s0 3d2. I usually don't write a subshell if it doesn't contain electrons, so you won't see me do this, but you will see this in textbooks, and maybe your teacher will insist on it. But yeah, that's a thing, just in case. There it is. So yeah, you subtract the outer electrons first. You take away from the valence electrons first, and then you start taking away from the inner electrons as you get closer and closer to the nucleus. So in fact, you can also make a titanium-4 ion. You can make a titanium-4 ion. And the configuration for titanium-4 is just going to be the configuration of argon. If you just write a noble gas as your configuration, that doesn't really count because it doesn't take much effort. So typically, teachers will expect you, if it has a noble gas configuration, to at the very least use the previous noble gas. So something like this, instead of writing just argon. But yeah, now we actually have a little bit of a reason for why transition metals can have multiple different charges. Oh, there's a reason behind all the Roman numeral stuff. There's a reason why transition metals can form different kinds of cations. There's a reason why you can have an iron 2 ion and an iron 3 ion. It's all about having some s electrons that get lost before the d electrons do. Sometimes you only lose the s electrons, in which case you can get a positive 2 charge. And sometimes you lose the s electrons along with some d electrons, in which case you can get positive 3 charges or higher. So yeah, there's actually a reason for it. Now the behavior of transition metals, at least when it comes to the ions, to the ions they form, at least when it comes to the ions they form, there's now a little bit of a reason for why transition metals are the way they are. Of course, it's not that much cause for celebration, because even with this newfound understanding, you're still going to see some weird behavior for transition metals in terms of their electron configurations and electron diagrams. So this doesn't fully solve the puzzle, but it gives you a little bit of a hint as to why you have multiple possible electron configurations. Not electron configurations, ionic charges. I'm looking at my notes and reading from them at the same time that I'm talking. Silly me. Let me think here. Was there anything else that I wanted to show? No, I don't think so. Let's take a look at... Yeah, let's just take a look at some problems and see which ones are worth going through. Problem 31 is asking, how are the Bohr model and the quantum mechanical model of the hydrogen atom similar, and how are they different? Well, the main similarities between the Bohr model and the quantum mechanical model is the existence of energy levels. So you still have this concept of n values starting at 1 and being associated with how close you are to the nucleus. And outside of that, there's not much similarity. That's not true. There is another bit of similarity in that electrons do have fixed energy levels, except they're average energy levels rather than discrete energy levels. I mean, they're discrete averages. But yeah, those are the only similarities I can think of. Anything else? Nothing's coming to my mind. 32. What are the allowed values for each of the 4 quantum numbers, n, l, ml, and ms? I already described those. N can be an integer, 1 or greater, L can be an integer 0 or greater, has to be less than n for a given electron. M sub L can be any integer between negative L and positive L. M sub S is plus or minus 1/2. 33, describe the properties of an electron associated with each of the following 4 quantum numbers. What? Oh, okay, I see. So they're asking, like, what's the meaning of each of those? We listed those. N is distance / average energy for the electron. L is the shape of space. M sub L is the orientation of that shape. And M sub S is the electron spin, the orientation of the magnetic field that an electron generates. 34 wants us to answer a couple of questions. Without using quantum numbers, describe the differences between shells, subshells, and orbitals. I think we've already talked about that. 35, identify the subshell in which electrons with the following quantum numbers are found. A, n equals 2, L equals 1, so that would be the 2p subshell. N equals 4, L equals 2, that would be the 4d subshell. N equals 6, L equals 0, that would be the 6s subshell. Pretty simple stuff if you've been paying attention. 36, which of the subshells described in the previous question contain degenerate orbitals? How many degenerate orbitals are in each? So, except for the s subshell, all of the other subshells have degenerate orbitals. The p subshell has 3 degenerate orbitals. The d subshell has 5 degenerate orbitals. The f subshell has 7 degenerate orbitals. Okay, so those are quick, like, check your understanding conceptual questions. What else do I have here? I don't think I'm going to answer these, but I'll put them on screen in case you'd like some more practice. But we've already done all of this stuff. Is there anything unique here? Oh, and they want you to do things the hard way here. No noble gas configurations. They want complete subshell notation. But yeah, we've already done this stuff, so I'll just leave it up on the screen so you can take a screenshot or whatever and use it as practice, or pause the video or whatever. Or maybe you feel you don't need the practice, which is fine too if you really do have a solid grasp on this. 50 is a rather unique question. It's asking if the electron configuration is the symbol for a macroscopic property or a microscopic property of an element. Explain your answer. This question kind of feels out of place to me. I did notice it when preparing the slides earlier, but I don't get why they're asking this. It is a microscopic property, but macroscopic versus microscopic properties, it would have been more appropriate for them to ask that sort of question in the gas laws chapter. In the gas laws chapter, things like pressure, volume, temperature, those are macroscopic properties. They're properties that make sense for a collection of particles, an entire system of particles, and don't really mean much for individual particles. A microscopic property of a gas particle would be, for example, the speed of a specific particle. The speed of a specific particle, or the kinetic energy of a specific particle, would be a microscopic property. A macroscopic property would be something like the temperature, which tells you the average kinetic energy and the average speed of the whole system of particles. But yeah, that's a weird out-of-place question, but in case you were curious about it, it's a microscopic property. It's a property of an individual atom that has that specific electron configuration. An electron configuration doesn't necessarily apply to all the atoms in a system, because if I had, like, say, I don't know, a container full of oxygen atoms, maybe some of those oxygen atoms are excited and their electrons have a configuration where the electrons are located in places above the minimum energy levels, in a place that violates the Aufbau principle. Then you could say that the electron configurations don't apply to the whole entire system of oxygen atoms, but only to specific ones. But yeah, that was a weird, out-of-place question, so I don't blame you for being confused by it. 51. What additional information do we need to answer the question, which ion has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6? So if you look at that, you can't tell which ion it is unless you know what its charge is. If you don't know how many electrons were lost to get to that configuration, you can't really tell, because that could be the configuration of titanium-4. That could be the titanium-4 configuration, or maybe it's the calcium configuration, the configuration for the calcium ion. When it loses both of its 4s electrons, it's left with a neon 3s2, 3p6. It could be the potassium ion after having lost one electron. So multiple different ions can have the same configuration, and most ions will have the configuration of a noble gas. Most ions will have the configuration of a noble gas, so you do need to know the charge. Knowing the configuration is not enough. And yeah, 52 is drawing diagrams. We've seen that. Let me see. What about these problems? 53, use a diagram to describe the electron configuration of the valence shell. We've done that. So again, this is just extra practice if you want it. 54, predict electron configurations for ions. Again, be careful with the cations especially. Write the configuration for the neutral atom first, and then subtract electrons from the valence shell first. So for example, if you have your valence shell as the fourth shell, and you've got a 4s and a 3d and a 4p, first you remove from the 4p, then you start removing from the 4s. Then if you still haven't removed enough electrons, that's when you start removing from the 3d. And then the 3p, and then the 3s, and so on and so forth. Other than that, nothing else to say about those. Anything interesting about these? Just identifying neutral atoms by their configuration, that's pretty doable. There they've got the configuration of an ion, but they also told you the charge of the ion, so you can figure out what it is. And 58. Which of the following atoms contains only 3 valence electrons? That one would be pretty interesting to look at, but I think you already know how to do it. I already showed you how to count valence electrons with my chlorine and bromine examples. Both of them had 7 valence electrons. Just count the total number of electrons in valence subshells. Those are the subshells that have the highest n values written in front of them. So yeah, most of this is pretty easy stuff, and what's really great about it is that it's non-calculator. You finally get to take a break from the calculator. You don't get to take a break from math, but at least you don't have to plug and chug with the calculator. 59. Which of the following has 2 unpaired electrons? So for questions like this, you need the electron diagram, not the electron configuration. And you have to be careful about when they ask this about things like chromium, molybdenum, copper, and silver. Those were some of the exceptions to the pattern that I talked about earlier. Number 60, which atom would be expected to have a half-filled 6p subshell? So half-filled, that would be 6p3, so figure out which atom ends in 6p3 basically. And you can just do that by reading off of the periodic table. Right, you can just, let's see, because this is 2p, 3p, 4p, 5p, 6p3, that's bismuth. I don't think you can read that very clearly, especially because of the, what do you call it, the sleeve or whatever this thing was called, the sheet protector. But you can read it on your own periodic table and confirm that it is indeed bismuth. Okay, 61, similar logic. Look for the 4s1. Look for the atom that's at the 4s1 location, so that would be 4th row, 1st column, potassium. 62, we've got in one area of Australia the cattle did not thrive, blah blah blah. Write the electron structure of the 2 cations. I'm guessing they mean the electron configuration, and yeah, that we've seen that. So we used titanium as our example of a transition metal. There's just another example with cobalt if you need more practice. And finally, these are the last of the problems I had. 63, we've got thallium can form +1 and +3 charges. Okay, so kind of like the cobalt problem, again, it's it's just recognizing the order in which you remove electrons is not the same as the order in which you fill electrons. Remove electrons from the valence shell first, and of course look at the possible different, what do you call them? Possible different ionic charges that you can get for those transition metals. Thallium is technically not inside of the D block, but it still counts as a transition metal. Same thing with lead and bismuth, in fact, and I think possibly indium and tin. But you can confirm that stuff with Wikipedia. Number 64, write electron configurations. We've seen that before. 65, cobalt-60 and iodine-131 are radioactive isotopes commonly used in nuclear medicine. How many protons, neutrons, and electrons are in atoms of these isotopes? Write the complete electron configuration for each isotope. Okay, so I'm not sure why they're asking you to count protons, neutrons, and electrons in this particular chapter. I would expect to see this kind of question either in one of the introductory chapters where we first talked about mass number and atomic number. I think I did that in part 2 of the series. Or I would expect them to have this in the nuclear chemistry chapter, where neutrons and protons and electrons and their counts are kind of important. But I wouldn't expect to see this here, so I'm skipping that first part of the question because it's not relevant to the chapter. The second part, write the complete electron configuration for each isotope. Isotopes have the same number of protons and electrons. What they have different is the number of neutrons, and the number of neutrons does not affect our electron configurations. If you still have the same number of electrons, then the electron configuration should not depend on which isotope you have of a particular atom. So 65, just write the standard electron configurations for cobalt and iodine the way you normally would, and don't overthink it. 66, write a set of quantum numbers for each of the electrons with an n of 3 in a scandium atom. Oh, okay, so so each of the third level scandium electrons. So scandium would have, let's see, it would have a full 3s subshell. Okay, let's actually do this one. Wait, that's not right. Okay, there we go. Yeah, let's actually do this one. I think I'll just do it on here so that I don't have to waste a new paper. So I'm going to write not the full electron configuration for scandium, but I'm not going to go too far in abbreviating it. So scandium, I'll start with neon rather than argon, and then have 3s2, 3p6, 4s2, 3d1. Yeah, 3d1. Okay, so you've got 2 plus 6 plus 1. You've got 9 different electrons for the scandium atom, and it basically wants us to give the 4 quantum numbers for each of them. I guess you could just make a table. All of them have n equals 3, so I'm going to skip on n. N is 3 for all of them. L is going to be 0 for those 2 electrons. M sub L is going to be 0 for both of those electrons. And M sub S, the spin, that is not an M. M sub S is going to be 1/2 for one of them and -1/2 for the other. Okay, that takes care of the 3s. All of them have n equals 3. For the 3p, so you're going to have L equals you're going to have L equals 1, and you're going to have 6 electrons with L equals 1, and I think you get the gist of it. So ML, you're going to have 2 electrons with -1, 2 electrons with zeros, 2 electrons with +1, and then 1/2, -1/2, 1/2, -1/2, 1/2, -1/2. Whoops, not -2, -1/2. Let me separate those into individual rows. So yeah, that should be more readable. And yeah, you can follow pretty much the same thing for the Oh, there's only one 3D electron, so I guess I can fill that in the remaining space I have. So for the 3D electron, for the one and only 3D electron that we have, n equals 3, L equals 2. ML, you have your choice here between -2 and +2. You can pick any of the 5 numbers, -2, -1, 0, 1, and 2. I'll just go with -2. And you can take your pick of which spin you want it to have, positive or -1/2. I'll just go with +1/2. And there you go. So there's a set of 4 quantum numbers for each of your electrons. Now that I think about it, I probably shouldn't have bothered writing 1 6 times here. I probably should have just had a single 1 right there. But, you know, that's what happens when you rush into things and don't pause to plan. It still works. Okay, so that wasn't too bad. There is one type of question that I did not see here, and I was pretty sure I had it included, but I guess not, so let me pull it out of my main book, and then with that we will wrap up, so it looks like I'm using a new sheet of paper after all. Let me grab... There was a really good problem in this book about... here we go. So, I have a table of quantum number values, and it wants us to write which orbital goes with the quantum numbers given. And if it's a violation, write that it's not allowed. So let's see. We have a table of N, L, and ML values. So here's what we've got. 2, 1, -1. 1, 0, 0. 3, -3, 2. 3, 2, -2. 2, 0, -1. Let me stretch this table out some more. Straight zeros. 4, 2, 1, and 5, 3, 0. And 5, 3, 0. And they told us for the first one, the answer is 2p. So that just kind of helps clarify what it is they want us to do. Okay. So, of course, if we see something that's not allowed, we should state that it's not allowed. So, n equals 1, L equals 0, M sub L equals 0. That's perfectly allowed. That is the 1s subshell. The one and only orbital in the 1s subshell. 3, -3, 2. So, if you remember all of the rules about how N and L and ML are related to each other, you might realize that an L of -3 is not valid for 2 reasons. One, because L values are never negative, but also because even if this was a +3, L has to be less than N. So L could either be 2 or 1, or it could be 2, 1, or 0, but It can't be positive 3, and it certainly can't be negative 3. So this one, not allowed. Not applicable. 3 to negative 2. Does this work? L is less than n, so that works. And then m sub L is somewhere between negative L and positive L, so that also works. So 3 and 2. 2 would correspond to a d subshell, so that's 3d. We're talking about one of the orbitals in the 3d subshell. 2, 0, negative 1. Does this work? Well, 0 is less than 2, so that's fine. This is not. M sub L has to be between negative L and positive L. Between negative 0 and positive 0, the only number you can have is 0. You can't have negative 1, not applicable. 0, 0, 0. You can't have this because you can't have n equals 0. N has to be a positive integer. It has to be 1 or larger. 4 to 1, does this work? 2 is less than 4, that's fine. And 1 is between negative 2 and positive 2, so that's also fine. So yeah, 4 and then 2, that would be a d subshell. It's one of the 4d orbitals. And then 5, 3, 0. So 3 is less than 5, that works. 0 is between negative 3 and positive 3, that works. So 5 and then 3 corresponds to F. Okay, and there you go. I think that should be everything for the basics of the quantum mechanical model of the atom and the electronic structure of the atom. In the next video, we will make use of this stuff. We will make use of electronic structure to help explain and justify certain properties that atoms have and how those properties vary as you move across the periodic table. We just saw in this video how the structure of the periodic table is directly related to the filling of the orbitals. So it wouldn't be a surprise if there are some more patterns that we see across the periodic table as a result of this. We'll dig into that stuff next time, and we'll also start talking about how to draw Lewis symbols and Lewis structures, the stuff that you've probably been waiting for since, I think the first video actually was where I mentioned Lewis structures. So yeah, we're getting there. We're getting to the part where we get to draw molecules. Oh, what fun. And the best part, no calculators. So yeah, that's what you can look forward to for next time. Let me see, do I have any other comments I'd like to make? Nothing in particular comes to mind, so yeah, I'll just wrap things up here. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I'll see you in the next video.